The Big Bang is our best story of creation, but it begins with a warning. Our equations break, and time itself loses meaning. Before the first atom, before the first second, there's a hard edge to physics, a boundary we can describe but not cross. So what could possibly trigger a beginning, and how would we ever prove it wasn't just an untestable myth? Before the first atom, before the first second, before space meant anything at all, physics runs into a wall. The Big Bang explains our earliest readable moment, yet it does not explain why there was a moment to read. In the deepest images of the cosmos, every galaxy is fleeing from every other, space itself is stretching. Run that expansion backward, and the universe grows hotter, denser, stranger, until even atoms cannot exist. Go farther still, and nuclei fall apart, matter dissolves into a quark, gluons see, and familiar laws begin to lose their grip. The Big Bang is not an explosion into empty darkness. It is the evolution of geometry, described by a scale factor that changes with time. This model stands on evidence that does not blink. The Hubble, Lemaitre law written in redshift, the cosmic microwave background glowing at 2.7 Kelvin, and the light elements forged in primordial fire. Together they tell a coherent story of a hot beginning. Yet they also point to a limit where the story stops being classical. Because when Einstein's equations are pushed to the edge, they return a warning, singularity, not a photograph of an actual place. It is a sign that something is missing, a regime where space-time may not behave like a smooth stage at all. And if time itself is part of the system, then asking what came before may be more than difficult. It may be the wrong kind of question, asked in the wrong language. Still, physics does not retreat from boundaries. It interrogates them. If the Big Bang was a transition, what was it a transition from? If it was a beginning, what rule selected it? If it was neither, what deeper description makes beginning an emergent word rather than a fundamental fact? In this journey, we will follow the universe back through its measured milestones, then step beyond them into ideas that risk sounding like philosophy, until they make predictions. We will meet quantum proposals where nothing has a technical meaning, inflationary scenarios that may be a prelude rather than an origin, and bounce models that replace a first moment with a turning point. We will confront the arrow of time, because any origin story must explain why the universe started in such an exquisitely low entropy state. And we will keep one demand fixed, even when the concepts grow strange: evidence. Before we dive into this cosmic puzzle, let's take a moment to appreciate the scale of it all. This story is travelling across the globe, reaching you right now. I'm always curious to see our small planet mapped out in the comments, so let me know which part of the world you're joining this exploration from. And if you believe these cosmic stories are worth exploring, the best way to support our mission is by liking this video and subscribing for the next one. The early universe left messages in the sky, in the pattern of microwave ripples, in the distribution of galaxies, and perhaps in gravitational waves that pass through matter untouched. Somewhere in those traces may be a signature of what our equations cannot yet name. Subtle, contested, and measurable in principle if we learn how to listen carefully enough. The Big Bang may be the first chapter we can currently read. That does not guarantee it was the first chapter that exists. We will begin by defining what the Big Bang model truly claims, then rewind toward the first second until geometry itself becomes uncertain. From there, we will test competing origin stories against the only judge cosmology recognizes, what the universe still allows us to observe. Before the first atom, before the first second, before space had any familiar meaning, physics points to a boundary where our equations stop. We call that story the Big Bang, yet the name misleads almost everyone, because it sounds like a blast in an empty void. The phrase suggests debris flying outward from a center, like a firework expanding into darkness. The model says something stranger and more precise, and it asks us to picture geometry rather than shrapnel. It describes space itself expanding from an early hot, dense state, with every region carrying its own rulers and clocks. In modern cosmology, the Big Bang is not a single event we watch happen, framed by an external camera. It is a framework that connects observations today to a past state inferred by well-tested physics and careful statistical reasoning. General relativity supplies the core rulebook for how matter and energy shape spacetime, and it does so with ruthless clarity, Under the assumption that the universe is homogeneous and isotropic on large scales, the FLW metric describes a cosmos that can expand or contract. That assumption is not blind faith. It is supported by galaxy surveys showing that, beyond clusters and filaments, the distribution smooths out. The scale factor becomes the key variable, telling us how distances between comoving galaxies change with time, even when those galaxies themselves are not moving through space. When we run that scale factor backward, the universe becomes smaller, hotter, and denser, and the numbers rise with startling speed. Temperatures climb until atoms cannot exist, because electrons cannot remain bound to nuclei in such an energetic bath. Push earlier, and nuclei cannot survive either, because high-energy photons tear them apart as fast as they form. Earlier still, even protons and neutrons dissolve into a quark-gluon plasma, a state recreated for fleeting instants in particle accelerators. This is not an explosion into pre-existing space, and it is not a ball of matter expanding into surrounding emptiness. It is the stretching of the metric, so every large-scale region sees others receding without a unique center, like dots on a balloon that has no privileged point on its surface. That distinction matters because our central question depends on it, and because intuition is easily hijacked by everyday metaphors. If space is what expands, then asking what is outside it may be meaningless, like asking what lies north of the North Pole. If time itself is part of the dynamical system, then asking what happened before may be ill-defined, because before presumes a time parameter that already exists, yet the urge to ask remains because the equations point toward an apparent beginning, and the mind resists boundaries. The documentary follows that tension between what the model actually claims and what our intuition demands, and it treats that tension as a clue rather than a flaw. Historically, this framework did not arrive as a single revelation, and it did not win by rhetoric. In the 1920s, Georges Lemaitre connected Einstein's equations to the observed redshifts of galaxies, arguing for an expanding universe when many still preferred a static cosmos. Edwin Hubble's distance measurements, though rough by modern standards, reinforced the idea that farther galaxies tend to show larger redshifts. Later, the debate sharpened into a competition between the Big Bang picture and the steady-state model, which proposed continuous creation to keep density constant. The turning point came not from philosophy, but from a prediction that could be checked against the sky. 3 observational pillars hold up the standard picture, and each one ties directly to the idea of an early hot, dense universe. The first pillar is the expansion of the universe, revealed by galaxy redshifts and the systematic stretching of light. Light from distant galaxies arrives shifted to longer wavelengths, and the stretching grows with distance in a pattern that is not random. The Hubble-Lemaitre law summarizes the trend, showing recession speed proportional to distance for nearby galaxies, where the relation is cleanest. Visually, the data look like a rising line through a cloud of points, with scatter that reflects galaxy motions inside clusters and the uncertainties of distance ladders. Redshift alone could be interpreted in several ways, including tired light or unknown photon effects, and early critics explored those alternatives. The power of the expansion picture is that it fits into GR and the FLRW metric, and it links to other evidence without special pleading. In an expanding universe, wavelengths scale with the scale factor, and so does the temperature of a thermal radiation bath. That means a universe that is cooler today must have been hotter yesterday, and the relationship is mathematically simple. Expansion also implies a finite look-back time to hotter epochs, which sets up testable relics rather than uncheckable stories. The redshift data therefore becomes more than a catalogue of moving galaxies. It becomes a clock and a thermometer for cosmic history. To make that clock feel real, imagine a deep field image where thousands of galaxies crowd a patch of sky smaller than a fingernail. Each faint smear is not merely far away in space, but far back in time. Because light takes time to travel, the most distant galaxies appear younger, bluer, and more irregular, because we see them when star formation was intense. The expansion history encoded in redshift tells us how quickly the cosmic stage grew, and it constrains what kinds of matter and energy must be present. Even the fact that the expansion rate changes over time becomes a measurable feature, not an assumption, when we combine different distance indicators. The second pillar is the cosmic microwave background, a prediction that once sounded almost too neat. If the early universe was hot and dense, radiation and matter were once tightly coupled in a plasma, with photons scattering constantly off free electrons. In that era, the universe was opaque, more like the interior of a star than a transparent void. As the universe expanded and cooled, electrons and nuclei combined into neutral atoms, a process called recombination, though it was really the first stable combination. Photons then decoupled and began free streaming through space, carrying with them a snapshot of conditions at that moment. Those photons should still exist today, cooled by expansion into microwaves, and spread across the sky in every direction. The CMB is that relic radiation, observed as an almost perfect blackbody spectrum at about 2.7 Kelvin, with a precision that is hard to overstate. A blackbody curve is not just a pretty fit, it is the fingerprint of a system that once reached thermal equilibrium. When instruments like COBA measured that spectrum, the result was a decisive blow to steady-state ideas, because it matched the hot origin prediction so well. On screen, the spectrum appears as a smooth arc, with data points hugging the curve as if guided by a ruler. Then the visuals shift to a full sky map, where faint mottling replaces uniform colour, revealing tiny temperature differences. The CMB does more than confirm a hot origin, because its tiny anisotropies map the seeds of later structure. Their angular pattern encodes the geometry and contents of the universe, including the balance between ordinary matter, dark matter, and radiation. Acoustic peaks reflect sound waves in the primordial plasma, compressions and rarefactions driven by gravity and pressure. Frozen, at last, scattering. The overall uniformity shows that the early universe was remarkably smooth, with fluctuations at the level of 1 part in 100,000. Yet those small ripples are everything, because gravity amplifies them over billions of years into galaxies and clusters. The CMB therefore anchors the Big Bang model in a detailed statistical snapshot of the universe, when it was only about 380,000 years old. The third pillar is primordial nucleosynthesis, the production of light elements in the first minutes, when the universe was hot enough for nuclear reactions. In a hot early universe, protons and neutrons interconvert until weak interactions freeze out, locking in a neutron fraction that will later feed helium production. As the temperature drops further, deuterium can survive without being immediately photodissociated, and that survival acts like a gate. Then nuclear reactions build helium and trace amounts of other light nuclei in a brief window before the universe cools too much. The predicted abundances depend mainly on the baryon to photon ratio and the expansion rate, which controls how quickly reactions shut down. Observations of hydrogen, helium, deuterium, and lithium provide a stringent check, because these elements are measured in environments chosen to be as chemically pristine as possible. The successes are striking, and they connect radically different eras into one consistent account. The universe is mostly hydrogen, with about a quarter of its mass in helium, and the deuterium abundance matches the value inferred independently from the CMB. These agreements lock together minutes after the Big Bang with hundreds of thousands of years after, and with the universe we see today in stars and gas clouds. Lithium remains an anomaly, with observed amounts below the simplest predictions, and that tension is informative rather than embarrassing. It signals either astrophysical processing in early stars, missing nuclear physics in reaction rates, or hints of new early universe ingredients. Even where the model strains, it does so in a way that invites sharper tests, because the discrepancy is specific and measurable. Taken together, these pillars establish a coherent narrative that is difficult to mimic with ad hoc alternatives. Space expands according to GR on large scales, and the expansion is visible in the systematic redshifting of light. A hot early phase leaves behind a cooled thermal background, and that background's spectrum and anisotropies match quantitative expectations. Nuclear reactions in the first minutes set light element abundances that persist, and their values depend on parameters we can cross-check. This is why cosmologists say the Big Bang is our best description of the early universe, even while they argue about details. It is not a guess about metaphysical beginnings, and it is not a myth dressed in equations. It is a model that earns its authority by matching multiple independent datasets with a small set of parameters. Yet the same mathematics that makes the model powerful also reveals its limit, and it does so with uncomfortable honesty. If we extrapolate the FLRW solution backward far enough, densities and curvatures grow without bound, and the energy scales approach realms we cannot reproduce directly. In classical GR, that trend leads to a singularity, often labelled T equals 0, where the scale factor goes to 0 in finite time. But t equals 0 is not a filmed moment in time, and it is not a physical object we can point to in space. It is the edge of the model's applicability, where the equations signal that new physics is required. This is where language becomes dangerous, because words smuggle in pictures that the math does not support. People hear singularity and imagine a point in space where everything was packed, like matter squeezed into a dot. The FLRW singularity is not a location inside the universe, and it is not a hidden corner where the laws of physics start. It is a statement that the classical description breaks down as we push it beyond tested regimes, much as fluid equations fail when we zoom down to individual molecules. Near that boundary, quantum effects of spacetime itself should matter, because gravity is no longer weak and smooth. We do not yet have a complete experimentally confirmed theory of quantum gravity, and without it, we cannot claim a final answer. Without it, the extrapolation to arbitrarily early times is not a prediction. It is a warning label. So what does it mean to say the universe began, and what kind of beginning do we actually have evidence for? One meaning is modest and operational, and it is the meaning scientists can defend in public without hand-waving. It means our reliable description begins at some early time, when known physics can be applied with confidence, and when the relevant interactions are understood. We can reconstruct conditions back to fractions of a second using particle physics, thermodynamics, and GR, and we can test those reconstructions against the CMB and element abundances. In that sense, the beginning is the beginning of a well-supported timeline, not necessarily the beginning of existence. Another meaning is existential, and it is the one that keeps returning in late-night conversations and in quiet moments under a dark sky. It asks whether time and space themselves came into being, or whether something preceded the hot, dense phase in a form our current theories only hint at. The documentary's central mystery lives in the gap between those meanings, because that gap is where explanation turns into interpretation. The Big Bang model tells us how the universe evolved from an early hot, dense state, and it tells us why relics like the CMB exist. It does not, by itself, tell us what caused that state, or whether cause is even the right concept when time may be part of what is emerging. When we ask what created the Big Bang, we might be asking several different questions at once, and each question carries its own hidden assumptions. Did time have a first moment, making before a category error, like asking what happened earlier than the earliest possible time? Did a quantum process nucleate a universe from a prior state described by a wave function, where probabilities replace certainties? Did a previous contracting phase bounce into expansion, replacing a singularity with a turnaround that leaves subtle scars? Or is our observable universe one bubble in an eternal inflating background, where beginnings are local and endings are rare, and where our patch is not the whole story? The possibilities differ, but they share a common feature. They push against the boundary where our tested equations fall silent. Each possibility changes what evidence could exist, so the question is not only philosophical, but observational. If there is no before, then the search is for internal consistency and for signatures of quantum gravity near the earliest accessible times, where classical space-time may blur. If there was a quantum beginning, we look for imprints in primordial fluctuations, non-Gaussianity, or specific tensor spectra that would act like a fossil record. If there was a bounce, we look for departures from standard initial conditions, perhaps in large-scale anomalies or relic gravitational waves that carry information through the transition. If there is eternal inflation or a multiverse, we ask what predictions remain and how to avoid explanations that fit anything, because science cannot live on flexibility alone. At this stage, it is crucial to separate what we know from what we hope, and to notice how the two interact. We know the universe is expanding, and we can measure the rate with multiple methods that mostly agree, though not perfectly. We know the CMB exists, and we can map it with exquisite precision, turning microwaves into a cosmological blueprint. We know light element abundances broadly match nucleosynthesis in an early hot phase, and we can trace how later stars modify those abundances. We also know that dark matter and dark energy dominate the cosmic energy budget, and that the simplest Big Bang story does not explain their nature. These unknowns do not erase the model's successes, and they do not license cynicism. They remind us that cosmology is built on both data and inference, measurements anchored to theories that remain incomplete. The phrase Big Bang therefore names two things at once, and the documentary insists on keeping them distinct. It names the hot early universe that is strongly supported by evidence, including the CMB and the light elements. It also names the formal limit where our classical equations stop being trustworthy and where new physics must take over. Confusing those two leads to false certainty and false skepticism, because it turns a successful model into a claim it never made. The goal of this chapter is to pin down what the Big Bang really says and what it does not say, using the pillars as guideposts. Only then can we ask what could have started it without smuggling in wrong assumptions, like an external clock or an outside space. We are left with a boundary that is both physical and conceptual, and it deserves to be approached with care. Physical, because extreme densities demand quantum gravity, and because energy scales near that boundary may unify forces in ways we have not confirmed. Conceptual, because time and causation may not extend past that boundary in the way we expect, and because our language evolved for mid-sized objects. The next step is to walk backward through the earliest moments we can reconstruct, using the evidence still accessible today, and using equations that have survived every test we can throw at them. From there, we can see exactly where the trail ends, and what kinds of clues might survive from anything earlier, faint patterns in primordial fluctuations, or subtle signatures in gravitational waves. To ask what started the Big Bang, we first have to learn how far the Big Bang lets us see. We start with the universe we can measure now, because the present is our only laboratory, and every inference about the past must pass through today's data. Space is expanding, and the expansion is accelerating. An empirical result stitched together from supernova distances, galaxy surveys, and the CMB's geometry. We name the driver dark energy, not because it is mystical, but because its microphysical origin remains unknown. That acceleration matters because it changes how distances grow, and it changes how we infer the past from present-day patterns. On screen, imagine a grid painted across space, with galaxies riding the grid rather than racing through it. This is the visual logic behind the expanding universe. In the FLW picture, we do not picture an explosion into pre-existing emptiness. We adjust a single bookkeeping variable, the scale factor, and we watch what must happen to temperature, density, and the typical energy per particle. As the universe contracts in time, photons blue shift, particle energies climb, and interactions that are rare today become unavoidable in a hotter, denser bath. Redshift is our practical dial for this rewind, because it is what telescopes actually measure. Higher redshift means we see light emitted when the scale factor was smaller, and when the cosmos was younger by a calculable amount. Looking far away is also looking back, because light takes time to cross expanding space, and that travel time is written into the spectrum. When a spectral line slides toward the red, it is not only a colour shift, it is a timestamp. The cosmic microwave background is the cleanest marker on that dial, and it is also one of the most visually striking scientific maps ever made. Today it is a 2.725 Kelvin blackbody, almost perfectly uniform across the sky, with tiny mottled variations at the level of tens of microkelvin. That temperature is not arbitrary, and it is not a property of space itself in isolation. It is the cooled remnant of a much hotter radiation bath that once dominated the universe's energy budget. Run the clock backward and the CMB warms as 1 over the scale factor, because stretching space stretches photon wavelengths in lockstep. At redshift around 1100, the radiation temperature was roughly 3000 Kelvin, comparable to the surface of a cool star. That number signals a threshold where atoms can finally survive, because thermal photons stop being energetic enough to ionize hydrogen efficiently. In plain terms, the universe cools past a point where electrons can stay attached. Before that threshold, the universe is a plasma of nuclei, electrons, and photons, more like the interior of a star than the emptiness we picture today. Photons scatter constantly off free electrons through Thomson scattering, a process with a well-measured cross-section. The mean free path is tiny, so the universe is opaque to light, and any beam is quickly randomized into a thermal glow. If we could stand there, an impossible thought experiment, we would not see distant objects, only a bright, uniform fog. Recombination happens about 380,000 years after the hot beginning we infer, although that moment is really a finite interval with a measurable thickness in time. Electrons bind to nuclei and form neutral atoms, mostly hydrogen and helium, as the ionization fraction collapses. The key result is not chemistry, even though the word sounds chemical. The key result is transparency, because neutral atoms do not scatter photons nearly as efficiently as free electrons do. When electrons become bound, photons stop scattering efficiently and begin free streaming, and the universe suddenly becomes a place where light can travel for billions of years. That releases what we call last scattering, and it sets a horizon for electromagnetic observation. The CMB is therefore a surface in time, not a wall in space, and we see it in every direction because we are inside the expanding sphere of that ancient glow. It is a photograph of a young universe, taken with the only camera nature could build. That surface also carries a map of early fluctuations, and the map is not decorative, it is dynamical evidence. Tiny temperature anisotropies encode density variations and acoustic waves in the plasma, driven by the competition between gravity and radiation pressure. Overdense regions try to collapse, photons push back, and the plasma rings like a drum, leaving a harmonic pattern in the CMB power spectrum. Those ripples later grow into galaxies and clusters through gravity, and their statistical fingerprints still match what we observe. Now we rewind, earlier than recombination, into the plasma era. Matter and radiation are tightly coupled, and pressure fights gravity on small scales, preventing immediate collapse. The universe is simpler in composition, but more extreme in conditions, and it behaves like a relativistic fluid. In visuals, the clean CMB sphere dissolves into a glowing, turbulent medium, bright, dense, and everywhere at once. As we go earlier, the energy density rises steeply, and the scaling laws become the narrator's compass. Radiation energy scales as the fourth power of temperature, so small changes in scale factor matter enormously. Meanwhile, number densities rise as the inverse cube of the scale factor, so particles crowd together as the universe shrinks. The early universe is therefore a high-energy particle system, not a dilute gas, and equilibrium is maintained by relentless collisions. At these times, the particle horizon becomes central to what we can claim, because causality is not optional in physics. The horizon is the maximum distance light could have travelled since the beginning of the expansion, given the finite speed of light and the finite age. It limits causal contact, and it limits what any region could have equilibrated with, even if interactions are fast locally. A universe can be hot and still fail to share information globally, simply because there has not been enough time. The horizon also clarifies a common confusion about seeing the beginning, because farther does not automatically mean earlier in an opaque medium. We can see back to the CMB with light because the universe becomes transparent then, and transparency is a physical phase change. Earlier than that, photons are trapped, so electromagnetic astronomy cannot go further, no matter how large the telescope. The limit is not engineering, it is scattering. If we want earlier messengers, we need particles that decouple sooner, meaning they stop interacting and begin free streaming earlier in the timeline. Neutrinos are one candidate, because they interact only weakly, and their interaction rate drops rapidly as the universe cools. Gravitational waves are another, because space-time ripples can pass through plasma almost unhindered, barely noticing the charged particles. Each messenger would carry a different kind of record, and each record would be distorted in its own way. We keep rewinding, and the universe crosses another well-tested milestone, one that was predicted before it was fully confirmed. In the first few minutes, nuclear reactions build the light elements, and the cosmos briefly becomes a fusion reactor. This is Big Bang nucleosynthesis, and it is one of the strongest quantitative successes because it links microphysics to cosmic history with very few adjustable knobs. When the calculations work, they work for reasons we can test. At around 1 second, temperatures are near a few billion Kelvin, and weak interactions begin to freeze out, because expansion starts outrunning reaction rates. Neutrons and protons stop interconverting efficiently through beta processes, and the neutron-to-proton ratio begins to drift mainly by neutron decay. The neutron fraction at freeze-out sets the helium yield, because almost every surviving neutron ends up bound into helium-4. In the visuals, think of a cooling furnace where certain reactions simply cannot keep up anymore. As the universe cools further, deuterium becomes stable against photodissociation, because the typical photon energy drops below the binding energy, often enough for deuterons to survive. That moment is sometimes called the deuterium bottleneck breaking, and it is a bottleneck for a simple reason. Without deuterium, there is no efficient pathway to build heavier nuclei in this environment, so the universe must wait for the temperature to fall. Once deuterium survives, Fusion chains rapidly build helium-4 and smaller traces of helium-3 and lithium. The nucleosynthesis window is brief because expansion wins, and the win is measurable in the final abundances. After roughly 20 minutes, densities and temperatures drop too far for efficient fusion, and the reaction network shuts down. The element ratios then fossilize, later modified mainly inside stars, where gravity can compress matter again and restart nuclear burning. It is a striking thought. The universe had one early chance to set these ratios, and then it moved on. This part of the story is anchored in nuclear physics we test on Earth, which is why it carries unusual credibility for such ancient times. Reaction rates, binding energies, and decay lifetimes are measured in laboratories, and the same equations run inside stars and inside cosmological codes. The remaining cosmological inputs are few, including the baryon to photon ratio and the expansion rate, both of which are constrained by independent observations. When different datasets agree, the timeline becomes more than a narrative, it becomes a cross-check. Observations largely match the predictions, and the match is not vague. Helium is about a quarter of baryonic mass, and deuterium agrees with the value inferred from the CMB, which is an impressive link between minutes and hundreds of thousands of years. Lithium remains a tension, and it is a reminder that precision cosmology still has open problems, even in its most successful chapter. Is the discrepancy astrophysical, nuclear, or a hint of missing early universe details? What exactly are we overlooking? Rewind again to roughly 1 second, and neutrinos become the main actors because they are about to slip the plasma's grasp. Neutrino decoupling occurs when the weak interaction rate falls below the expansion rate, a competition between microphysical probability and cosmic stretching. After decoupling, neutrinos free stream, forming a cosmic neutrino background that fills space today, cooler than the CMB and vastly harder to detect. In principle, it is a relic sea passing through you right now. We have not directly detected that background yet, but its effects are indirect and measurable, which is often how cosmology works. Neutrinos alter the expansion history and the growth of fluctuations, because they carry energy and they move fast, smoothing structure on small scales. They also leave imprints in the CMB power spectrum and in large-scale structure, subtly changing the pattern of peaks and the clustering of galaxies. The data do not show neutrinos as a photograph, but as a gravitational influence. At this point, our timeline is still within known physics, but it is nearing the edge of direct tests, where confidence becomes conditional. We are using the standard model of particle physics in a thermal bath, and we are using general relativity to connect energy density to expansion. The logic is clean. Specify the contents, compute the pressure and density, and the Friedmann equations tell you how the scale factor evolves. Yet the farther back we go, the more we lean on extrapolation rather than direct experiment. Go earlier than a second, and temperatures exceed tens of billions of Kelvin, where rest masses are no longer the main scale. Electrons and positrons are abundant, and particle-antiparticle pairs appear and annihilate in equilibrium, constantly replenished by energetic photons. The universe is a collider that never turns off, until expansion cools it and the balance tips toward annihilation. When that happens, the plasma's composition changes, and entropy is redistributed among the remaining species. Earlier still, protons and neutrons are not stable composite objects in the way we know them, because the thermal environment overwhelms confinement. Quarks and gluons are deconfined in a quark, gluon plasma, a state of matter first seriously explored in theory decades before it was produced in laboratories. Heavy ion experiments recreate this state briefly, producing a tiny droplet that behaves like an almost perfect fluid, and that gives us confidence about its basic properties. Cosmology scales that droplet up to the size of the observable universe, while keeping the same underlying interactions. In that era, the relevant scale is not chemistry or nuclear binding, and it is not even the existence of atoms. It is quantum chromodynamics at high temperature, where confinement disappears and the degrees of freedom change. The universe is a fluid of fundamental fields, with transport properties like viscosity and diffusion that we can partly model. Even the phrase particle becomes context-dependent, because excitations in a hot plasma do not behave like isolated billiard balls. Keep rewinding, and we approach the electroweak era, where the familiar separation of forces begins to blur. At energies above roughly 100 Geiger, electron volts, the electromagnetic and weak forces unify into a single electroweak interaction, described by a shared gauge structure. The Higgs field's behaviour changes with temperature, reshaping particle masses, because mass in the standard model is not merely a label. In a hot enough universe, the symmetry is effectively restored, and the rules look simpler, even as the energies become more extreme. Here the documentary needs a careful distinction between tested and extrapolated physics, because confidence has a boundary. Collider experiments probe the electroweak scale directly, and they validate the standard model there with extraordinary precision. Cosmology uses the same equations, but applies them to an expanding background, where the experiment is the entire sky. That move is justified by consistency, yet it is still a move. That application is reasonable because the early universe is close to thermal equilibrium, which is a powerful simplifying fact. Interaction rates are fast compared to expansion at these energies, so particles share a common temperature, and chemical potentials remain well defined. The hot plasma therefore behaves like a system we can describe statistically, using distribution functions rather than tracking individual collisions. In other words, the chaos averages into predictability. Yet we are also approaching a gap, and it is not a small one, either in energy or in conceptual risk. Between the electroweak scale and the Planck scale lies an enormous range of energies, spanning many orders of magnitude. In that range, we suspect new physics, but we do not know its form, and we do not know which symmetries survive. It is a blank region on the map, marked only by theoretical signposts. The Planck scale is where quantum gravity should become unavoidable, because the characteristic energy density makes space-time itself fluctuate. It is around 10 in 19 giga, electron volts, far beyond any accelerator and far beyond any direct terrestrial test. If we push general relativity and quantum field theory without modification, our equations begin to contradict their own assumptions, because they treat space-time as both smooth and violently energetic at once. That contradiction is not a failure of math, it is a warning about domain of validity. This is the point where the rewind becomes a stress test, and the stress is physical, not rhetorical. General relativity links expansion to energy density through the Friedmann equations, and those equations are exquisitely successful at lower curvatures. As we go back, densities rise, curvature grows, and classical spacetime becomes an increasingly fragile approximation, like a map drawn on paper that starts to crumple. At some point, the variables we rely on may stop being the right variables. It is tempting to say we are approaching a literal beginning, because the language of the Big Bang invites that picture. But that is not what the evidence forces, and careful science is defined by what the evidence compels. The evidence forces a hot, dense early phase and a transparent surface at recombination, and it supports a sequence of thermal milestones. It does not force a singular start because singularities signal breakdown, not a confirmed physical event. To keep the logic clean, we separate 3 layers of claim, and we say them out loud. First, the observed universe expanded from a hotter, denser state, and the CMB and light elements confirm it with independent precision. Second, known microphysics explains key transitions back to at least the first second, including nuclear synthesis and neutrino decoupling. Third, beyond that, we extrapolate, and extrapolation is not the same as measurement. The particle horizon returns here as more than geometry, because it shapes the meaning of initial conditions. It tells us what could have been in causal contact, and it limits how uniformity can arise without additional mechanisms. It also hints at why inflation was proposed, because the CMB is uniform beyond naive horizon limits, and the observed flatness is unexpectedly precise. These are not aesthetic complaints, they are quantitative puzzles. Inflation is not the focus of this chapter, but it is a signpost that belongs on the roadside of any rewind. It is one of several ideas that extend the timeline earlier than the electroweak era, and it is motivated by specific observational tensions. Even if the details remain uncertain, the logic is instructive. Observations can demand new, early universe behaviour. The universe, in that sense, tells us what questions are worth asking. Other messengers could, in principle, carry information from earlier times, and they function like alternative senses. Primordial gravitational waves would encode the expansion history at extremely high energies, because their spectrum depends on how the scale factor evolved. Relic particles, like axions or other dark matter candidates, could freeze out and persist as cosmic fossils, preserving conditions from their decoupling epoch. Each candidate is a hypothesis with a test attached, and that attachment is what keeps it scientific. Neutrinos sit between these categories, because they decouple early but still within known interactions, which makes them especially valuable. Detecting the cosmic neutrino background would open a new observational window, not by replacing the CMB but by complementing it. It would push our direct timeline earlier than recombination in a tangible way, and it would tighten constraints on the first second. What would it feel like to confirm, experimentally, a relic that has been passing through Earth since before there was Earth? Gravitational waves could push even further, at least in principle, because they do not thermalize easily in plasma. Unlike photons, they are not scattered into equilibrium by electric charges, and they can propagate with minimal attenuation across cosmic time. If produced in the early universe, they could carry a record of phase transitions or inflationary dynamics, encoded as a faint background hum. The challenge is that the universe is loud with other signals, and the early whisper is hard to isolate. But every proposed messenger must answer the same hard question, and the question has two parts. What signal survives billions of years of expansion, and what detector could ever measure it with credible statistics? The central question stays scientific only if it stays tied to observable consequences, because otherwise it becomes a story we cannot falsify. In cosmology, imagination is useful, but measurement is the referee. So we pause and take inventory of what is solid, because the rewind is only as good as its anchors. Recombination is plasma physics and atomic physics in an expanding background, and its signature is the CMB's blackbody spectrum and anisotropies. Nucleosynthesis is nuclear physics plus a well-defined expansion rate, and its signature is the primordial element abundances. The electroweak era is particle physics at energies we have tested, extended to cosmological conditions where equilibrium makes the math tractable. Then we inventory what is not solid, but still structured, because uncertainty does not mean chaos. The gap between electroweak and Planck scales is a regime without direct experiments, and it is where many models compete. We can write theories there, we can compute consequences, and we can constrain them indirectly, but we cannot yet confirm which one nature uses. The map has contour lines, yet the terrain is not surveyed. This is where general relativity becomes both guide and warning, and the dual role is essential to the chapter's meaning. It is our best theory of spacetime dynamics, and it passes every precision test in its domain, from planetary orbits to gravitational waves. When extrapolated backward, it points toward a boundary where curvature diverges and time-like geodesics end, which is the mathematical signature of a singularity. The warning is that the theory itself tells us where it may stop speaking reliably. That boundary is why the documentary's hook is not just poetic, because the question is physical and sharp. Before the first atom and before the first second, the timeline becomes a question about spacetime itself, not merely about hotter matter. If the Big Bang is the earliest chapter we can read, we need to know what the book's binding is made of. Smooth geometry, quantum foam, or something we have not named. And if time has a beginning, what does before even mean in a theory where time is part of the system? The rewind has done its job if it leaves one clear impression, and the impression is a structured gradient of certainty. Established physics carries us from today back through galaxies, through the CMB, through nucleosynthesis, and to neutrino decoupling with confidence. Past that, the trail fades, and the fading is a measurable gap in energy scale, not a failure of curiosity. The universe is not hiding. Our tools are simply limited. Now the narrative turns from chronology to limits. The closer we get to the beginning, the more our reconstruction depends on general relativity's extrapolation, because gravity is the framework that turns energy into expansion. To ask what created the Big Bang, we must first ask what general relativity predicts when pushed to its edge, and whether that prediction is physical or pathological. The next step is not to add drama, but to add clarity. In the next chapter, we take that prediction seriously, and we examine what a singularity really means in physics. We will see whether it is an actual origin, a mathematical artifact, or a sign that time itself needs a quantum rewrite. We have rewound the universe to the edge of tested physics, where gravity runs the clock and geometry becomes destiny. General relativity is the rulebook that turns energy content into cosmic expansion, translating matter into curvature with strict accounting. When we push that rulebook backward, it issues a warning in the language of mathematics. In cosmology, we simplify the universe to its large-scale symmetries. because the sky looks statistically similar in every direction. We call those symmetries homogeneity and isotropy, and they are not aesthetic choices. They are empirical, grounded in surveys of galaxies and in the near-uniform glow of the cosmic microwave background. With those symmetries in place, we write the Floer metric, a compact way to encode space-time distances as the universe evolves. Homogeneity and isotropy reduce the problem to a single function, the scale factor AT, plus a discrete curvature label. The scale factor measures how co-moving distances grow, so it defines what we mean by expansion rather than motion through space. Visually, you can imagine a faint grid painted across the cosmos. Galaxies sit on the grid without needing engines. As time advances, the grid spacing changes, and the same coordinate separation corresponds to a larger physical distance. That is why expansion is not an explosion from a center, but a uniform stretching of the metric itself. General relativity connects that geometry to matter through Einstein's field equations, which relate curvature to the stress, energy tensor. Under FLRW symmetry, those equations become the Friedmann equations, which act like a dynamical balance sheet for the entire universe. They tell us how fast a changes, given energy density, pressure, and spatial curvature, and they do so without reference to any outside timekeeper. The first Friedmann equation ties the expansion rate to the total energy density and curvature, turning cosmic history into an initial value problem. In compact form, h squared scales with r/O, with an extra term from curvature k over a squared. The second equation shows how acceleration depends on both density and pressure, so it explains not only expansion, but whether that expansion speeds up or slows down. It helps to pause on the symbol h, the Hubble parameter, because it is more than a number measured today. ht is the fractional growth rate of the scale factor, telling you how quickly the cosmic ruler changes per unit time. When h is large, the universe's conditions evolve rapidly, and physical processes must race to keep up. That pressure term is the part intuition often misses, because pressure gravitates in GR rather than merely resisting compression. The reason is built into the stress, energy tensor, where pressure contributes to the source of curvature alongside energy density. In plain language, squeezing a fluid stores energy, and GR counts that stored energy as gravitationally active. For radiation, pressure is 1/3 of energy density, so it strongly affects deceleration in the early universe. For a cosmological constant, pressure is negative, which drives accelerated expansion by making the right-hand side of the acceleration equation effectively repulsive. This is not anti-gravity in a cartoon sense, it is the geometry responding to a stress pattern with POI and ZR. These equations are not optional assumptions because they are the GR consequences of the symmetries we have already committed to. Once you choose the contents of the universe, you can compute ρ and p as functions of AT using conservation laws. Then the equations tell you how the scale factor evolves and how temperature and density scale as the universe expands or contracts. Run the solution backward and the logic becomes stark, almost mechanical in its inevitability. As a T shrinks, number densities rise as 1 over a cubed. Because the same particles occupy a smaller volume, radiation energy density rises faster, as 1 over a to the 4th, because photons blue shift and each photon carries more energy. That extra factor of A is easy to visualize if you picture light waves stretched across space like ripples on an expanding sheet. As the sheet contracts in reverse, the ripples compress, wavelengths shorten, and the color shifts toward the blue and then beyond. The universe becomes a particle accelerator powered by geometry. No machine required. Temperature follows the same trend, scaling roughly as 1 over a in thermal equilibrium, because typical particle energies track the thermal scale. That means earlier times are not just denser, but hotter in a precisely calculable way. The early universe becomes a high-energy system because expansion itself sets the thermometer, and the Friedmann equations set the pace. This is why the rewind in earlier chapters felt inevitable rather than speculative, even before we discuss any particular particle model. Given expansion today, the Friedmann equations imply a hotter, denser past, and they quantify that implication with simple power laws. Given a thermal plasma, the scaling laws imply rising temperature and interaction rates, so the early universe becomes a laboratory for high-energy physics. As densities climb, collisions become frequent, and matter and radiation exchange energy efficiently. In that regime, equilibrium is not a vague metaphor. It means reaction rates exceed the expansion rate, so the plasma has time to settle into a thermal distribution. The moment expansion outruns interactions, species fall out of equilibrium, and the universe preserves fossils of that freeze-out. But the same extrapolation pushes GR toward an extreme conclusion, and it does so with unnerving mathematical consistency. For ordinary matter and radiation, the equations typically drive AT towards zero at a finite proper time in the past. Density, curvature, and temperature then blow up in the classical description, as if the universe is being forced into an impossible corner. That mathematical endpoint is what people call the Big Bang singularity, although the phrase can mislead if taken too literally. In the simplest models, it appears at t equals 0, where the scale factor vanishes and classical quantities diverge. It is tempting to treat that as a literal first moment, because the equations seem to demand it, and because the model's time coordinate runs out. We need to slow down here, because singularity is a technical word with a specific meaning in relativity. In GR, a singularity is not defined as a point of infinite density sitting somewhere in space, like a pinprick of matter. It is defined by geodesic incompleteness, meaning some space-time paths cannot be extended indefinitely, even though the laws are supposed to be deterministic. A geodesic is the path a free-falling observer follows when no forces act except gravity, and it is the relativistic generalization of an inertial trajectory. In a well-behaved space-time, you can extend such paths smoothly into the past and future, always finding earlier and later points. In a singular space-time, some of those paths simply end after finite proper time, as if the map of space-time stops providing coordinates. That ending is the key warning sign, because it means the space-time manifold is incomplete in the precise sense used by mathematicians. The theory is telling you that its own notion of time evolution breaks down, even for idealized observers who feel no forces. It is not automatically telling you that nature contains literal infinities, only that the classical description has reached a boundary. This is where the Penrose-Hawking singularity theorems enter the story, adding rigor to what the FLW equations suggest. They are not about special coordinates or perfectly symmetric toy models, and they do not rely on choosing a clever time variable. They show that, under broad conditions, GR generically predicts incompleteness, so the problem is not easily dismissed as an artifact of idealization. Historically, this was a turning point in the 1960s, when relativists began treating singularities as robust predictions rather than curiosities. Penrose first developed tools to analyze gravitational collapse. Then Hawking adapted and extended them to cosmology. The result was a deep and unsettling message. The breakdown is woven into the causal structure of spacetime, not merely into our equations' aesthetics. The theorems assume reasonable energy conditions, which roughly say energy density is non-negative for physical observers, and gravity tends to focus world lines. They also assume global features like trapped surfaces or sufficient focusing of geodesics, conditions that encode the idea that light cones can be squeezed. Under those assumptions, gravity makes geodesics converge, and convergence forces an endpoint because paths cannot be extended past a caustic without leaving the manifold. In cosmology, the relevant conclusion is that an expanding universe with ordinary matter tends to be past incomplete. Even if the universe is not perfectly smooth, the theorems still apply in many cases, because small irregularities do not undo global focusing. Classical GR then suggests a boundary to the past, not an eternal extension, and it does so without specifying what that boundary contains. That sounds like a beginning, and it is why the Big Bang is often described that way in popular language. But the theorems do not say what the boundary is made of, and they do not describe a physical mechanism that creates space-time. They also do not resolve what replaces the breakdown, because a theorem can prove incompleteness without providing the missing completion. They also do not say the universe began from a point in pre-existing space, which is a common but deeply misleading image. The FLW singularity is not a location inside the universe, because the universe is the space-time and there is no external container. The singularity is a limit of the description, where curvature and variance often diverge, and where the concept of earlier loses its footing. So what does infinite density mean in this context, beyond the emotional punch of the word infinite? It means the classical variables we're using have been pushed beyond their domain of validity, like extending a map beyond the edge of surveyed territory. It is like predicting infinite pressure at a point in a fluid, which usually signals that the fluid approximation has failed and that molecular physics must take over. Physicists treat infinities as red flags because they usually mark missing degrees of freedom, not because they fear large numbers. Classical electrodynamics once produced divergent self-energies for point charges, and quantum theory changed the bookkeeping by altering what point-like means operationally. In GR, the divergence suggests that space-time itself needs new microphysics, because the metric is being asked to remain smooth under conditions where quantum uncertainty should be unavoidable. A useful parallel comes from black holes, where GR also predicts singularities and where the same interpretive caution applies. In the Schwarzschild solution, curvature grows without bound at r equals 0, and tidal forces become arbitrarily strong. Yet the singular region is hidden behind an event horizon for distant observers, which changes what can be tested and what can be operationally defined. The horizon matters because it limits what can be observed and what can influence the outside, acting like a one-way causal membrane. Signals from inside cannot reach an external observer once they cross the horizon, no matter how powerful the emitter. The singularity is therefore not a place we can probe directly with light or particles, and that observational barrier shapes how physicists talk about reality inside. Cosmological singularities differ, because there is no external region watching from afar and no outside clock ticking independently. If the whole universe is involved, there is no external observer and no external time parameter to compare against. Still, the black hole case teaches a lesson about interpretation, because it shows how a singularity can be a limit of predictability rather than a tangible object. The lesson is that a singularity in the equations is not automatically a physical object you can point to on a diagram. It may be a boundary of predictability, where classical evolution cannot continue because the theory's assumptions fail. The horizon shows how GR can hide the breakdown while still giving accurate predictions outside, which is exactly how effective theories behave when they have a limited domain. In cosmology, we do not have a horizon that hides the early boundary from us in the same way, because there is no outside to stand in. We do have observational horizons set by recombination and by causal limits, which define how far back electromagnetic signals can carry clean information. Those horizons tell us what information can reach us, even if earlier physics existed, and even if the earliest boundary is not directly observable. This is where language about before the Big Bang becomes dangerous, because it quietly assumes a time coordinate that extends smoothly past the boundary. But in GR, time is part of the dynamical geometry, not an external parameter that always exists in the background. If the geometry becomes ill-defined, the time coordinate that depends on it may also become ill-defined. If space-time is geodesically incomplete, the theory does not supply a meaningful continuation of time, at least not within its own terms. Asking what happened before may be like asking for a page number before page 1, because the ordering concept itself is missing. The question might be undefined, not merely unanswered, and that distinction matters when we decide what a future theory must explain. Yet undefined is not the same as impossible, and it is not the same as meaningless in every theoretical framework. It means that within classical GR, the concept of earlier time may fail because time is inseparable from the metric. A deeper theory could still contain a prior phase, but it would redefine what time means and how earlier is encoded. To keep the logic clean, we separate coordinate artifacts from physical singularities, because relativity is full of misleading coordinates. Some singularities disappear when you change coordinates, like the apparent divergence at a black hole horizon in Schwarzschild time. Those are not real breakdowns because curvature invariants remain finite and freely falling observers cross without drama. A physical singularity is different, because it shows up in invariant quantities that no coordinate choice can hide. Curvature scalars can diverge, tidal forces can become unbounded, and geodesics can end in finite proper time. Those features cannot be removed by a clever choice of coordinates, which is why they are taken seriously as indicators of theoretical limits. The Big Bang singularity in standard FLRW models is typically of the physical kind, not just a coordinate glitch at t equals 0. It is tied to diverging density and curvature as E approaches 0, and it appears in invariants like the Ricci scalar for matter-filled universes. In the language of the model, every comoving observer sees the same approach to the boundary, which is why there is no privileged center. But even a physical singularity does not force us to accept literal infinities as real components of nature. It forces us to admit that classical GR cannot be the whole story at arbitrarily high curvature, because it cannot evolve beyond its own endpoint. It tells us where the theory stops making controlled predictions, and where new principles must enter. This is why many physicists describe singularities as indicators of missing physics, rather than as final answers. They are not satisfied with a theory that ends in infinities, because infinities block explanation and calculation. A good theory should replace the divergence with new, finite behaviour, while reducing to GR where GR has been tested. There is also a practical reason for skepticism about literal infinities, and it comes from quantum mechanics rather than from philosophical taste. Near the Planck scale, quantum fluctuations of fields become unavoidable, and the energy required to localize events becomes gravitationally significant. If energy is concentrated into a region small enough, quantum uncertainty and gravitational back reaction collide, undermining the smooth metric approximation. In that regime, treating spacetime as a smooth manifold may be the wrong approximation, even if it works beautifully at lower curvatures. The metric may fluctuate, topology may change, and the classical notion of a single trajectory may fail, because trajectory presumes a fixed background geometry. The singularity then becomes a signpost toward quantum gravity, pointing to a place where our familiar categories, space, time, and causality, may need revision. Even before we reach the Planck scale, we should notice how much extrapolation is being asked of GR when we run the clock backward. We have tested GR in weak and moderate fields, and we have tested the Friedmann framework through cosmological data across billions of years. We have not tested GR at arbitrarily high curvature, so intellectual honesty requires us to label the conclusion as conditional. So the honest statement is conditional, and it is still powerful. If classical GR holds all the way back, and if reasonable energy conditions apply, then the past is incomplete, and the classical description has a boundary. That is a profound result about spacetime structure, but it is not a final description of reality, because it explicitly marks the place where the theory stops. This is also where the central question sharpens, because the boundary changes what origin can mean. If the Big Bang singularity is a boundary of classical spacetime, then asking what created it may be the wrong framing, since creation is usually described as a process in time. The better question becomes what replaces that boundary in a deeper theory, and what observable consequences that replacement must leave behind. Some possibilities keep a beginning but change its character, replacing a classical first moment with a quantum condition. Time might emerge from a quantum state, with no classical notion of earlier and later at the deepest level, and with classical time appearing only when the universe becomes semi-classical. In that view, the beginning is not an event inside time, but a limit where time becomes meaningful, and where classical trajectories become a good approximation. Other possibilities replace the beginning with a transition, keeping the narrative of evolution but altering its earliest chapter. A prior contracting phase could bounce into expansion, avoiding infinite density if new physics provides an effective repulsion at high curvature. A quantum gravity correction or new degrees of freedom could prevent her from reaching zero, turning the singularity into a turnaround rather than an endpoint. Still, other possibilities suggest that our patch has a beginning, while a larger structure does not, so the word beginning becomes local. Eternal inflation can produce local hot Big Bang regions as bubbles, each with its own effective T equals 0 and its own reheating surface. The global picture can be past incomplete or not, depending on the model, which is why singularities remain an active frontier rather than a closed case. At this stage, we do not choose a favourite, because the chapter is about the warning sign itself and what it logically implies. GR tells us how to evolve the universe, given contents and initial data, and it does so with remarkable precision in regimes we can test. It also tells us that, under broad conditions, the classical evolution cannot be extended indefinitely backward, which is both a triumph of reasoning and a limit of the framework. That is both a triumph and a limitation, and the two are inseparable. It is a triumph because the theory makes a sharp, non-trivial statement about the structure of spacetime, not a vague handwave about beginnings. It is a limitation because the statement is the end of the classical road, not a complete origin story with a mechanism we can compute. So we return to what singularities mean and what they do not mean, because clarity here prevents years of confusion. They mean geodesics end, predictability fails, and curvature can diverge in the classical description, which is a precise technical diagnosis. They do not mean we have observed an infinite density point, or that physics has explained creation, or that the universe popped into existence like an object in a room. They also do not mean the universe exploded from a place inside space, because that picture smuggles in an external stage. The singularity is not a center, because every co-moving observer traces the same shrinking scale factor when the model is run backward. The boundary is in time within the model, not in space within the universe, and that is why every direction looks like away from us in expansion. This helps clarify another confusion about causation, which is usually defined within time as relations between earlier and later states. Causes in physics are typically local and temporal, embedded in differential equations that march forward. If time itself is part of what breaks down, then causation may need a new formulation, perhaps one that treats entire histories as the objects of prediction. That does not make the question unscientific, but it changes what counts as an answer, and it changes what evidence would look like. An answer might be a quantum law that assigns probabilities to entire histories, rather than a single chain of prior events. An answer might be a boundary condition that replaces a prior cause, specifying what is allowed at the edge of classical space-time. General relativity therefore hands us a choice, and it is not a matter of taste or storytelling preference. Either we accept a literal singular beginning, with infinities that resist interpretation and calculation, or we treat the singularity as a sign that the classical theory is incomplete, and we search for the next layer that keeps predictions finite. Most working physicists choose the second option, because it matches how physics has progressed before when theories met their own limits. When a theory predicts its own breakdown, we look for the next layer, guided by what the old theory did correctly. We do not declare the breakdown to be the final mechanism, because breakdown is not an explanation, it is a diagnosis. This is where the documentary's hook returns with sharper meaning, and with a more visual sense of what the equations are doing. Before the first atom and before the first second, the equations point to a boundary, like a horizon in time that our classical tools cannot cross. The boundary is not a wall we can photograph, but a limit we can infer from the way expansion, density and curvature are chained together. We can also ask what evidence could ever test ideas beyond that limit, because science advances by turning metaphysics into measurement. If quantum gravity modifies the earliest moments, it may change the spectrum of primordial fluctuations that later seed galaxies. It may leave signatures in gravitational waves, in non-Gaussian statistics, or in relic particles that carry information from energies we cannot reproduce on Earth. Even the absence of certain signals can be informative, because it constrains how violent the earliest phase could have been without spoiling what we observe. A bounce model must preserve the observed near-scale invariant perturbations, or it must explain why they look inflationary anyway. A quantum beginning must reproduce the CMB's precise pattern down to the acoustic peaks that encode the universe's early sound waves. So the singularity is not only a philosophical problem, but a research program with concrete targets and failure modes. It tells us where to look for new physics, and what a successful theory must recover at lower energies, including the Friedman behavior where GR is tested. Any replacement must reproduce the ordinary expansion history with exquisite accuracy, because the late universe is already a precision dataset. The chapter ends with a pivot from geometry to quantum principles, because the warning sign points directly at quantum uncertainty. If space-time itself becomes uncertain, then the universe must be treated as a quantum system, not merely as a classical stage with quantum actors. The next step is to ask what it means to quantize the cosmos, and what replaces classical time when time is part of the system. If classical space-time fails at the beginning, the next chapter asks what quantum space-time can do instead. General relativity brought us to a boundary where classical time and curvature fail, and the familiar equations stop giving reliable answers. Quantum cosmology asks whether that boundary is replaced by a quantum rule, something like a selection principle, rather than a literal first tick of a universal clock. On screen, imagine the smooth grid of space-time bending under mass, then tightening into a region where the grid lines blur and lose meaning. In classical relativity, a singularity is not simply a point in space, but a breakdown of the description itself. Geodesics end, curvature scalars can diverge, and the idea of before becomes physically undefined. We need to define nothing the way physicists use it, or the discussion collapses into wordplay. In physics, nothing is rarely philosophical non-being, and it is never a simple empty box. The term is a placeholder for specific limiting cases in a theory, each with its own mathematical structure. Sometimes nothing means a lowest energy state of quantum fields, the vacuum of a theory, which is still a state of something. In modern particle physics, the vacuum is defined relative to fields that fill all of space, even when no particles are present. It is the baseline configuration that cannot be lowered without changing the rules of the theory. Sometimes it means the absence of classical spacetime geometry, where distance and duration are not yet defined. That is a sharper claim than empty space, because empty space already assumes a metric, a causal structure, and a notion of separation. If there is no classical geometry, there is no classical stage on which events can be ordered. Sometimes nothing is a boundary condition in a path integral, where you sum over possible geometries. In that framing, the question becomes which histories are allowed, and with what weight. The emphasis shifts from a single beginning to a catalogue of possible beginnings, each assigned an amplitude. Even the vacuum is not featureless, because quantum fields have unavoidable fluctuations that are built into the formalism. The vacuum has a structure defined by the fields, their symmetries, and the rules of quantization. What looks like emptiness to classical intuition becomes a state with correlations, response functions, and measurable effects. The uncertainty principle is the first intuition, but it must be stated carefully to avoid a popular misunderstanding. It does not say energy can be created from nothing without constraint, and it does not guarantee a universe. In its precise form, it limits how sharply certain pairs of observables can be specified in a single quantum state. It says certain pairs of quantities cannot both be sharply defined in a quantum state, because their operators do not commute. If you constrain a system in time or in configuration, you broaden what can be known about conjugate variables. In plain language, a quantum system cannot be pinned down in every way at once. Vacuum fluctuations are better described as temporary variations in field values around an average, governed by the vacuum wave functional. They are not particles popping in and out as a literal mechanism, but a shorthand for correlations. When we compute what detectors would register, we are really calculating how fields respond to interactions and boundaries. A useful visual is a calm ocean surface that is never perfectly flat, even when there is no wind. The ripples are not objects appearing from nowhere, but the unavoidable jitter of the underlying medium. In quantum field theory, that medium is a set of fields defined everywhere, and the jitter is encoded in their ground state fluctuations. Vacuum energy is the second ingredient, and it is both powerful and confusing for good reasons. In quantum field theory, the ground state can carry energy, and that energy gravitates in general relativity. The stress-energy tensor does not care whether energy comes from particles or from a vacuum expectation value. Yet the observed cosmic acceleration implies a vacuum-like energy scale that is tiny by particle physics standards. The mismatch between naive estimates and observation is the cosmological constant problem. If you sum zero-point energies up to high frequencies in the most straightforward way, you get an answer that is catastrophically larger than what the universe appears to contain. Historically, this tension has been a guidepost rather than a footnote, because it signals that our bookkeeping is incomplete. Einstein introduced the cosmological constant as a term allowed by the equations, later called it a blunder, and then watched it return as a measured feature of cosmic expansion. In quantum theory, the same term becomes entangled with renormalization, regularization choices, and whatever quantum gravity ultimately demands. So quantum cosmology proceeds with humility about what vacuum energy means in a complete theory. It uses effective descriptions, while admitting that quantum gravity may change the bookkeeping. Effective field theory is powerful because it organizes what we can predict at accessible scales, but it is not a final verdict about the earliest moments. The central question returns in a sharper form that is easy to say and hard to formalize. If spacetime is quantum near the boundary, what counts as a cause when time itself is not fundamental? Causation is usually narrated as earlier producing later, but that grammar depends on a time parameter we may not be allowed to assume. One strategy is to treat the universe as a quantum system with a wave function, defined on a space of possible configurations. Instead of evolving a classical metric, you assign amplitudes to possible geometries and field configurations. The wave function is not a picture of a single universe, but a rule for weighting alternatives. This is where the Wheeler-DeWitt equation enters, as a formal attempt to quantize gravity canonically. It looks like a Schrödinger equation for the universe, but without an external time parameter. The equation arises from rewriting general relativity in Hamiltonian form, where constraints encode the theory's coordinate freedom. In that equation, the Hamiltonian constraint becomes an operator that annihilates the wave function, rather than generating ordinary time evolution. The result is the problem of time, because the fundamental equation is timeless. What we call time in everyday physics is tied to a choice of slicing space-time into moments, and that slicing is not unique. Time then becomes an emergent parameter, defined by correlations between degrees of freedom that can act as clocks. A clock is not outside the universe, so time is a relational variable inside the quantum state. One subsystem changes in a way that can be used to label change in another subsystem, and that labeling becomes the operational meaning of time. This is not just philosophy, because it changes what predictions look like in principle and in practice. Probabilities must be defined without assuming a background time that labels before and after. Even the language of initial conditions becomes delicate, because the theory may not privilege a first moment. A second strategy uses the path integral, summing over histories rather than evolving in time as a parameter. You compute an amplitude by integrating over possible geometries weighted by an action. In ordinary quantum mechanics, the path integral sums over trajectories, while in quantum gravity, it must sum over spacetime geometries themselves. In this approach, nothing can mean a boundary where the geometry closes off smoothly, with no edge to fall off. The universe is not created in time, but described by a complete history with a boundary condition. The boundary is not a moment in time, but a condition on the allowed geometries in the sum. The most famous version is the Hartle, Hawking no-boundary proposal, developed in the early 1980s when inflation was also taking shape. It replaces a sharp beginning with a smooth Euclidean cap, where time behaves like a spatial direction. Mathematically, the metric signature changes in a way that makes the geometry regular at the south pole of the history. Near the cap, the geometry is finite and regular, so the classical singularity is avoided in the semi-classical picture. Far from the cap, the history becomes Lorentzian and looks like an expanding universe. The transition is often described as a continuation from imaginary time to real time, though the interpretation depends on the chosen contour. Visually, the idea is often drawn like the rounded end of a sphere that gently turns into a trumpet-shaped expansion. There is no sharp corner labelled t equals 0, only a smooth closure where the classical notion of time fades. The point is not that the universe had a hidden earlier time, but that the classical coordinate fails near the cap. The proposal is often summarized as a universe with no initial boundary in time, only a smooth closure. The wave function assigns weights to different large-scale universes that emerge. Those weights depend on the action of the corresponding saddle points, which are approximate solutions dominating the path integral. But the details matter, because the path integral is hard to define rigorously in quantum gravity. One must choose a contour, a measure, and a set of allowed geometries, and each choice changes results. Even the question of which complex metrics to include can alter whether the wave function favours more or less inflation. A competing picture is Vilenkin's tunneling proposal, which uses quantum tunneling as the origin mechanism. The universe nucleates from a classically forbidden region into an expanding state. The language borrows from barrier penetration in quantum mechanics, but the coordinate is a geometric degree of freedom. In tunneling language, the scale factor behaves like a coordinate in a potential determined by curvature and energy content. Quantum mechanics allows a transition through a barrier, producing a small universe that then grows. In semi-classical terms, one computes an exponential suppression or enhancement from an instant and like solution. This is often described as creation from nothing, but nothing still means no classical spacetime, not absolute non-being. The proposal assumes a quantum framework in which such a transition is meaningful. It also assumes that the notion of a wave function over geometries is valid in the regime where classical spacetime does not yet exist. Both proposals try to answer the same problem left by Chapter 3, where classical theorems point to geodesic incompleteness. They replace geodesic incompleteness with a quantum boundary condition or a quantum transition. The singularity becomes less like a physical point and more like a signpost that classical variables have been pushed too far. They also share a delicate point that must be stated clearly, because it is where rhetoric often outruns physics. A wave function of the universe does not automatically explain why there is a universe. It specifies allowed histories. It is a law-like object that constrains possibilities, not a final explanation of existence. In quantum theory, explanation often means a rule that assigns probabilities to outcomes, given a state and dynamics. For cosmology, the outcomes are entire universes or entire histories, not repeated lab trials. That difference matters, because we cannot rerun the universe to gather frequencies in the usual way. That raises the measure problem, which is not a technical footnote but a structural challenge. If there are many possible histories, how do you define a probability distribution that is not arbitrary? The answer depends on what you count as distinct, how you regularize infinities, and which coarse grainings correspond to meaningful observations. In path integrals, the measure over geometries is ambiguous without a completed quantum gravity theory. In canonical approaches, the inner product on the space of states is also subtle. Without a well-defined notion of normalization, even the statement "this history is more likely" can become ill-posed. The absence of external time makes probability even harder to interpret, because time usually organizes conditional statements. In ordinary quantum mechanics, probabilities refer to measurement outcomes at time, conditioned on preparation. The laboratory provides an external clock, a clear separation between system and observer, and a repeatable protocol. In cosmology, there is no external observer preparing the universe and measuring it from outside. Any account must explain what counts as an observation inside a closed quantum system. Observers are physical subsystems, and their records are correlations stored in matter, radiation, and memory. Another challenge is that semi-classical approximations can smuggle in the very time they claim to derive. You often assume a background-like variable to recover classical evolution. The approximation may be justified when the universe is large and slowly varying, but it becomes questionable near the quantum boundary. So the honest claim is conditional and limited, even when the mathematics is elegant. These proposals show how a beginning might be replaced by a quantum condition, not that the issue is solved. They provide candidate boundary prescriptions whose consequences can be studied, compared, and potentially constrained. There is also the question of what nothing means when fields are present, because fields are not optional in modern physics. A vacuum state presupposes a theory with degrees of freedom, laws, and a notion of energy. Even to say lowest energy, you need a Hamiltonian, and that already encodes structure. Even no classical spacetime can still involve a quantum gravitational structure, rather than a blank void. It might be a foam of geometries, a discrete network, or something not yet defined. The important point is that physics can describe a limit where classical geometry disappears, but it still describes something with rules. So the chapter draws a boundary between rhetoric and physics, which is a boundary worth defending. Physics can model a lowest energy state, a boundary condition, or a tunneling event, but not absolute non-being. When popular accounts say from nothing, they often mean from no classical spacetime, and that is a very different claim. The next step is to connect these ideas to evidence, because cosmology is not only metaphysics with equations. A viable origin proposal must reproduce the observed hot Big Bang phase. It must connect an abstract wave function, or path integral to a universe filled with radiation, matter, and the thermal history we can reconstruct. That means it must yield an expanding universe with the right contents and the right perturbations. It must match the CMB's acoustic peaks, the near-flat geometry, and nucleosynthesis. These are not aesthetic preferences, but quantitative benchmarks that any early universe model must hit. Quantum cosmology often predicts a distribution of initial conditions for the scale factor and fields, rather than a single deterministic start. Those initial conditions can influence curvature, fluctuation spectra, and the likelihood of inflation. In practice, the wave function is used to compute relative weights for different semi-classical histories. Here, the visuals can shift to the cosmic microwave background as a mottled sphere, where tiny temperature variations encode primordial statistics. Those variations are only one part in 100,000, yet they carry a fossil record of early quantum fluctuations. The question becomes whether a proposed beginning naturally yields the observed near-scale invariant pattern. This is where quantum origin scenarios meet a practical bridge, because the bridge is dynamical as well as conceptual. Many of them rely on a rapid early expansion to produce a large, smooth universe like ours. Without such an expansion, the models can struggle to explain why distant regions look so similar and why spatial curvature is so small. Inflation is not just an add-on for beauty. It is a mechanism that makes initial conditions less special. It stretches space, dilutes curvature, and can turn quantum fluctuations into classical seeds. The fluctuations begin as vacuum correlations on microscopic scales, then get pulled to astronomical sizes where they later guide structure formation. A vivid way to picture this is to imagine a tiny patch of space, smaller than an atom, being blown up until it spans light years. The quantum jitter in that patch becomes a pattern written across the sky, later amplified by gravity into galaxies and clusters. Inflation, if it occurred, is the translator between quantum microphysics and cosmic architecture. But inflation also inherits the measure problem in a sharper form, especially in eternal inflation scenarios. If inflation produces many regions, probabilities depend on how you count them. Different cutoffs and counting rules can lead to different predictions, which means the theory needs a principled measure to be predictive. So quantum cosmology and inflation are entangled, even when treated as separate topics for clarity. The origin proposal sets the stage, and inflation often supplies the early dynamics. The boundary condition can influence whether inflation starts, how long it lasts, and what spectrum of perturbations it produces. We should also acknowledge the missing foundation under all of this, because the honesty of the subject is part of its scientific character. A complete quantum gravity theory is not yet established, and different approaches disagree on basic structures. We can write down candidate equations and integrals, but we do not yet have a universally accepted definition of the underlying degrees of freedom. String theory, loop quantum gravity, causal sets, and other programs offer partial tools and partial insights. Quantum cosmology borrows techniques, but it cannot yet claim a unique settled framework. The same boundary proposal may look different or even become ill-defined when translated into a different quantum gravity language. That is why the chapter emphasizes what these models are for and what they are not for. They are controlled thought experiments that translate what caused the beginning into calculable boundary conditions. They let us ask a sharper question. Given a rule for amplitudes, what kinds of universes are favoured? They also show what kind of evidence might matter, which is where the story becomes testable rather than purely speculative. Primordial gravitational waves, non-Gaussianity, or specific anomalies could support or constrain families of initial states. Even the absence of expected signals can be a powerful discriminator, because it forces models into narrower corners. Even null results are informative, because they rule out large classes of early histories. Precision limits on tensor modes already shape which inflationary and quantum origin models remain plausible. Each improved measurement tightens the allowable space of initial conditions and pushes theory toward more specific commitments. We end where we began, with the boundary between readable history and inferred origin. The Big Bang may be a hot phase that follows a quantum condition, not the absolute start. The earliest chapter of the universe might be written not in classical time, but in a quantum rule that only later yields a classical clock. The central question remains open, but it becomes sharper and more testable as our data improve. If nothing is a physical state or boundary condition, then it can leave fingerprints in the sky. The challenge is to connect those fingerprints to a well-defined measure and a well-defined quantum theory of space-time. Now we pivot to the next chapter's engine, because many origin stories depend on it. To understand quantum beginnings in practice, we have to understand inflation and what it explains. Inflation is the bridge between a quantum origin and the hot Big Bang we can measure, and it is also a hypothesis with specific observational targets. Inflation is the bridge between a quantum origin and the hot Big Bang we can measure. It is also a hypothesis with specific observational targets and specific ways to fail. If the bridge is real, it should leave a consistent set of traces, and those traces are what we look for next. Inflation enters the story as a proposed prelude to the hot Big Bang, not a replacement for it, and it claims the universe briefly expanded at an accelerating near-exponential rate very early on. The motivation was not philosophical comfort, but specific puzzles inside the standard hot Big Bang picture. Puzzles that show up as mismatches between simple equations and a remarkably orderly sky. In the late 1970s and early 1980s, as particle physics and cosmology began speaking the same language, these puzzles sharpened into a challenge. The Friedmann-Lemaitre equations worked beautifully, yet they seemed to require special initial conditions. The microwave background looked too uniform, space looked too flat, and exotic relics predicted by high-energy theories refused to appear. Inflation was proposed as a dynamical way to make those features natural, at least within a broad class of early universe histories. Start with the horizon problem, which is really a causality problem written on the sky. The The cosmic microwave background is uniform to about 1 part in 100,000 across vast angles, even between regions separated by tens of degrees. In a simple radiation-dominated rewind, widely separated regions were never in causal contact before recombination. They should not share the same temperature without a mechanism that allowed earlier communication. To picture the issue, imagine the CMB as a spherical photosphere surrounding us, glowing from when the universe was about 380,000 years old. That glow is thermal radiation, so its smoothness implies earlier mixing and equilibration, like a gas reaching a common temperature. Yet in the non-inflationary hot Big Bang, light signals cannot cross the needed distances in time. The sky looks as if it coordinated its temperature faster than causality allows. Inflation changes the causal diagram by stretching a once-connected patch into the entire observable universe. Before inflation ends, regions that later look disconnected were close enough to equilibrate through ordinary microphysics. After inflation, that shared history is frozen in as near uniform temperature, with only tiny residual variations. The CMB then becomes a fossil of a small, once causal domain enlarged beyond intuition. A more technical way to say this is that inflation makes the co-moving Hubble radius shrink, even while physical distances grow rapidly. Modes that were once comfortably inside the horizon are pushed outside it, so they stop exchanging information. The universe becomes smooth not because it keeps mixing, but because it stops needing to. What we observe as large-scale uniformity is the memory of an earlier time when large-scale meant microscopic. Next is the flatness problem, which is a stability problem in the Friedmann equations. Spatial curvature behaves like a term that grows in importance relative to matter and radiation as the universe expands. To get today's near-flat geometry without inflation, the early universe must start extraordinarily fine-tuned. The required tuning becomes more extreme the earlier you set the initial conditions. The observational statement is simple. The total energy density is extremely close to the critical density that separates open from closed geometries. In the standard hot Big Bang, any slight deviation from that balance tends to grow with time, rather than wash out. That makes near flatness look like a precarious balancing act performed at the earliest moments. The question is not whether flatness is possible, but why it seems so stable in reality. Inflation drives the curvature term towards zero by rapidly increasing the scale factor. Exponential expansion makes any initial curvature negligible, the way a small bump looks flatter on a balloon as it inflates. Flatness becomes not coincidence, but an attractor-like outcome for a wide range of starting conditions. The universe can look geometrically simple, even if it began messy. The visual here is almost deceptive because the effect is so strong. A patch that begins with noticeable curvature can be stretched until its radius of curvature is vastly larger than the observable universe. Locally, that looks indistinguishable from Euclidean space, the geometry of a ruler and a right angle. Inflation does not prove the universe is exactly flat, but it explains why any curvature would be hard to detect. A third motivation is the absence of unwanted relics predicted by high-energy theories. Grand unified models often produce magnetic monopoles and other heavy defects in the early universe, especially during symmetry-breaking phase transitions. In a non-inflationary hot Big Bang, those relics would be abundant and hard to hide. We do not observe them, despite decades of searches in cosmic rays, lunar samples, and specialized detectors. The monopole problem is partly a lesson in how seriously cosmology takes particle physics. If a theory predicts a stable, massive object, and the early universe reaches the energies where it forms, then the universe should be full of it. Monopoles are not just missing, they are missing by an enormous margin. That mismatch suggests either the underlying high-energy theory is wrong, or the universe's thermal history is not as straightforward as the simplest picture. Inflation dilutes relics by expanding space so dramatically that any initial density becomes negligible. Monopoles can exist yet be so rare that none appear within our observable volume, even if they were produced. This does not prove inflation, but it makes inflation a practical fix for a real overproduction problem. It also reframes relic searches as tests of how much early expansion occurred. So inflation begins as a set of repairs, but it quickly becomes a predictive framework. It requires a mechanism that produces negative pressure and nearly constant energy density for a short time. In general relativity, accelerated expansion happens when pressure is sufficiently negative, because pressure gravitates as well as energy density. The simplest way to model that is with a scalar field. The inflaton is a hypothetical scalar field whose energy is dominated by potential energy. When the field rolls slowly on a flat potential, its energy density stays nearly constant, and its pressure becomes negative. A near-constant energy density acts like a temporary cosmological constant, though it is not necessarily the same as today's dark energy. The Friedmann equations then yield rapid, accelerating expansion. Slow roll is more than a metaphor, because it is encoded in parameters that compare the slope and curvature of the potential to the expansion rate. If the potential is too steep, the field races downhill and inflation ends almost immediately. If it is sufficiently flat, the field's kinetic energy stays small, and the vacuum-like behavior persists. In plain terms, the field must loiter long enough for space to stretch by an enormous factor. This is the core physical picture. Even though the microphysics is still unknown, the inflaton is not automatically the Higgs, not automatically a string modulus, and not automatically anything we have measured. It is a placeholder for a degree of freedom that can drive a brief vacuum-like phase. The success of the idea depends on consequences, not on naming the field. The number of e-folds is often used to quantify how much inflation occurred, because exponential growth is naturally measured in logarithms. Roughly 60 e-folds is the canonical target for solving the horizon and flatness problems for our observable region. More e-folds make the universe smoother and flatter, but they also make it harder to connect inflation to specific initial conditions. Even the bookkeeping becomes part of the conceptual story. Inflation must also end because our universe becomes hot and radiation-filled. Ending inflation requires the field to leave the slow-roll regime and convert its energy into other degrees of freedom. That conversion is called reheating, though it can include complex intermediate stages and resonant particle production. The essential claim is that inflaton energy becomes particles and radiation. Reheating is not merely a cleanup step because it determines what the universe is made of when the hot Big Bang begins. The temperature after reheating controls which particles are produced, which symmetries are restored, and how subsequent phase transitions unfold. It also affects subtle observables, because the expansion history between inflation and nucleosynthesis leaves faint fingerprints. Reheating is where inflation hands off to the hot Big Bang we already trust. In this view, the hot Big Bang is not the absolute beginning. It is the aftermath of inflation's ending, when a cold, vacuum-like state becomes a seething plasma. Visually, the chapter's palette shifts from an empty, rapidly stretching space-time to a universe suddenly filled with light and scattering particles. The familiar thermal story starts here, with temperatures and reaction rates we can model. That shift matters for the central question of what created the Big Bang. If the hot phase begins at reheating, then asking what started the Big Bang becomes asking what started inflation. Inflation moves the boundary of ignorance rather than erasing it, and it does so in a way that is partly testable. It also offers new observables that can point back toward that earlier boundary. The most important observables are the tiny primordial perturbations that later form galaxies. Inflation predicts that quantum fluctuations of fields and space-time get stretched to cosmic scales, turning microscopic uncertainty into macroscopic structure. Modes begin deep inside the horizon, behave like vacuum fluctuations, then exit the horizon during inflation. Later, after inflation ends, they re-enter and seed structure. The remarkable claim is that the seeds of galaxies are, in a precise sense, amplified quantum noise. During inflation, each mode is stretched until its wavelength exceeds the horizon, at which point its amplitude effectively freezes. After re-entry, gravity amplifies over densities and matter flows into them, eventually forming the cosmic web. The large-scale distribution of galaxies is therefore a late-time echo of early-time quantum statistics. This mechanism produces a nearly scale-invariant spectrum of density perturbations. Nearly scale-invariant means fluctuations have almost the same strength on many length scales, so the universe has no preferred size for its initial clumps. The deviation from perfect scale invariance is measured by the spectral index, which is sensitive to how slowly the inflaton rolls. Observations find a slight tilt, consistent with slow-roll inflation rather than exact scale invariance. Amplitude matters as much as tilt, because it sets the overall contrast of the early universe. The measured scalar amplitude is small, about 1 part in 100,000, yet it is not arbitrary. In inflation, that amplitude reflects the energy scale and the shape of the potential, filtered through the expansion rate. A universe with slightly larger fluctuations would collapse too quickly, while a universe with smaller ones might remain nearly featureless. Inflation also predicts the perturbations are close to Gaussian. Gaussianity means the statistics are mostly captured by the two-point correlation function, or equivalently the power spectrum, much like random noise characterized by its variance. Non-Gaussianity would show up as significant higher-order correlations, revealing interactions or multiple fields during inflation. Many inflation models predict small but potentially measurable departures, and the data constrain them tightly. Another key prediction is that the fluctuations are adiabatic rather than isocurvature. Adiabatic means different components fluctuate together, preserving relative number densities at fixed total density, so the perturbation is a curvature perturbation. Isocurvature would mean components fluctuate against each other, leaving different signatures in the CMB peaks and in large-scale structure. The observed acoustic peak pattern strongly favours adiabatic initial conditions. These predictions connect inflation to the precision structure of the CMB. The anisotropies are not random noise but a mapped imprint of primordial statistics, processed by well-understood plasma physics. The peaks and troughs in the angular power spectrum arise from sound waves in the photon, baryon fluid, frozen at recombination. When we look at the CMB, we are effectively looking at a snapshot of oscillations caught mid-cycle. Cope first detected large-angle anisotropy, confirming fluctuations existed at the expected level and giving cosmology its first quantitative handle on primordial seeds. WMAP refined the acoustic peak measurements and tightened cosmological parameters, turning the CMB into a high-precision dataset. Planck then pushed precision to the point where inflation-like predictions became sharply testable. With Planck, the sky's faint mottling became a set of numbers with error bars small enough to exclude broad classes of models. Planck measured the spectral index and confirmed it differs from one at high significance, matching the expectation of a slightly imperfect scale invariance. It found the fluctuations are very close to Gaussian and strongly adiabatic, with non-Gaussianity constrained to be tiny. It also constrained spatial curvature to be very small, consistent with inflation's flattening effect. The overall picture is not a single proof, but a coherent alignment of independent signatures. This is the strongest observational support for inflation as a general idea. The universe appears to have started with the kind of perturbations inflation naturally produces, and the CMB's statistics look like the output of a simple early mechanism, yet the same data do not uniquely select one inflation model. Many different potentials and mechanisms can fit the same broad observables, because several microphysical stories can generate similar effective slow-roll behaviour. The most sought-after discriminant is the tensor component, primordial gravitational waves. Inflation generically produces tensor fluctuations from quantum fluctuations of the metric itself, not just of matter fields. Those tensors imprint a specific pattern in CMB polarization, because they shear spacetime in a way scalar modes cannot. The target is a curl-like pattern called B-modes. Polarization is subtle, but the visual is crisp when mapped. E-modes form gradient-like patterns, while B-modes twist into swirls. Primordial B-modes would peak on degree scales, corresponding to horizon-sized patches at recombination. Their amplitude would reveal the inflationary energy scale, because stronger inflationary expansion produces larger tensor fluctuations. A clean detection would therefore connect cosmology to physics at energies far beyond any accelerator. A detection of primordial B-modes at the right angular scales would be a smoking gun for inflationary tensors. It would measure the energy scale of inflation and narrow the space of viable models, especially those with large field excursions. It would also connect early universe cosmology to quantum gravity questions, because it would be a direct signature of quantized spacetime perturbations. But the signal is hard because foreground dust and lensing can mimic or obscure it. So far, experiments have not confirmed primordial tensor B-modes. The tensor-to-scalar ratio, R, is constrained to be small by combined CMB measurements, including polarization and temperature data. Those limits already rule out simple high-field models with a large predicted tensors, the early textbook examples. They push model building toward lower tensor amplitudes, more complex potentials, or alternative mechanisms that keep tensors suppressed. This is where we separate what is confirmed from what remains open. Confirmed is that the primordial spectrum is nearly scale invariant, slightly tilted, and close to Gaussian and adiabatic. Confirmed is that the universe is very nearly flat within current errors, and that it began with tiny coherent perturbations. Confirmed is that the hot Big Bang began in a state consistent with inflation-like initial conditions. Not confirmed is the inflaton's identity, its potential, or even whether a single scalar field is the right description. Not confirmed is the detailed reheating history and the temperature at which the hot phase begins, which affects how inflation connects to particle physics. Not confirmed is the tensor signal, which would anchor the energy scale with far less degeneracy. Not confirmed is whether inflation is the only mechanism that can produce similar perturbations. Inflation also carries conceptual costs that become unavoidable at this stage of the documentary. It can make the universe less sensitive to initial conditions, but it can also make the origin question harder to close. If inflation can start in many ways, then explaining why it started becomes a new frontier. If inflation is generic in high-energy landscapes, then it may be difficult to define probabilities. The measure problem appears again, now sharpened by expansion that can create enormous volumes. If inflation lasts long enough, different regions can realize different outcomes, even with the same underlying laws. Counting those outcomes can depend on how you regulate infinities in space-time volume, because eternal expansion produces endless copies of events. Predictions can become ambiguous without a principled measure. There's also the question of initial conditions for inflation itself. Slow roll requires a patch that is smooth enough and dominated by potential energy, and that requirement can sound like a new fine-tuning. Some argue inflation makes such patches likely, because expansion quickly erases gradients once inflation begins. Others argue it assumes what it tries to explain, because the patch must already be special enough to start inflating. The debate is technical, but the narrative point is simple. Inflation may solve some fine-tunings while introducing others at a deeper level, shifting rather than eliminating the need for explanation. When we ask why the CMB is smooth, inflation answers with dynamics. When we ask why inflation began, the answer is less settled, and that uncertainty is part of the chapter's tension. Then comes the possibility that inflation is not a single event, but an ongoing process. In many models, quantum fluctuations of the inflaton can keep some regions inflating, even as others end, because the field's value can wander upward in some patches. Regions that end inflation reheat and look like hot Big Bang universes, with matter, radiation, and a local arrow of time. Regions that keep inflating continue to spawn more reheating regions. This is eternal inflation, and it changes what a Big Bang means. A local hot Big Bang becomes a transition surface inside a larger inflating spacetime, more like a phase boundary than a universal beginning. Our observable universe becomes one bubble or one reheated patch among many, separated by distances that expand faster than light can traverse. The word beginning becomes local, and the global story becomes harder to define. Eternal inflation also returns us to the question of whether inflation itself had a beginning. Some theorems suggest inflating spacetimes are past incomplete under broad conditions, meaning you cannot extend all geodesics indefinitely into the past. Past incomplete sounds like a beginning again, but it may be a boundary of description rather than a first event. The mathematics tells us the classical picture cannot be the whole story, yet it does not tell us what replaces it. So inflation can be both a leading clue and a possible detour. It is a clue because it predicts the perturbations we observe with striking accuracy, and it ties those perturbations to a simple physical mechanism. It is a detour if it postpones the origin question, without making it more testable, especially if it opens a multiverse of outcomes. The documentary's central question demands we keep both possibilities in view. At this point, the narrative tightens around what inflation actually buys us. It explains why the observable universe looks smooth across the horizon, even where naive causality would fail. It explains why curvature is so small, and why relics can be absent, without requiring impossible initial balancing. It provides a mechanism for the seeds of structure that matches the CMB's statistics with extraordinary precision. But it also shifts the origin question to a new layer: what prepared the inflating patch, and what set the inflaton on its potential, at the right place and with the right smoothness. What selected the parameters that control the tilt, the amplitude, and the reheating outcome, which then shape every later epoch. What, if anything, makes inflation start rather than not start? This is where the earlier chapters connect directly to the next ones. Chapter 3 showed classical spacetime can be past incomplete, forcing a boundary or new physics beyond the classical equations. Chapter 4 explored quantum boundary conditions that might replace a classical beginning, offering proposals rather than settled answers. Inflation now sits between those ideas and the hot Big Bang we measure, acting as a possible translator from quantum beginnings to classical heat. If inflation happened, it may be the bridge from a quantum origin to a classical thermal universe, because it can take a tiny patch and make it look macroscopic and smooth. If inflation did not happen, something else must reproduce its successes without its assumptions, and it must do so with the same numerical precision. Either way, the sky's tiny fluctuations become our most direct evidence about the earliest accessible physics. The question becomes whether that evidence points to one beginning, many beginnings, or a deeper rule that makes beginnings emergent. We end this chapter by turning the bridge into a new challenge. If inflation can be eternal, then our Big Bang may be one of countless reheating events, each with its own local history and perhaps its own effective constants. If inflation must have a beginning, then we still face a boundary where time and causation may fail, at least in classical terms. The next chapter follows that fork, asking whether many Big Bangs are a prediction or a warning. Now the story pivots from inflation's successes to its most unsettling implication. If inflation is real, did it ever truly start, or does it never fully end? Inflation solved problems by stretching one small patch into our observable cosmos, smoothing curvature and diluting relics as space expanded at an extraordinary rate. It also opened a deeper question about what inflation does globally, beyond the horizon of any single observer. In the simplest story, inflation ends everywhere, and reheating starts the hot Big Bang, as if a single cosmic switch were flipped. In many realistic models, that ending is not synchronized across all space, because the mechanism that ends inflation is itself a physical process with local variation. The inflaton is a quantum field, so its value cannot be perfectly uniform, even if it is nearly uniform on large scales. Quantum fluctuations add random kicks on top of the classical slow roll, and those kicks are unavoidable, because the field is subject to the uncertainty principle in an expanding spacetime. Visually, imagine a gently sloping landscape seen from above, smooth in outline, yet rippled by tiny restless waves. Those ripples represent fluctuations in the inflaton's value, and during inflation they are continuously stretched until they become variations from one Hubble-sized region to another. Most regions drift downhill and eventually exit inflation, converting vacuum-like energy into particles as the inflaton's energy is transferred to other fields. Those regions reheat, thermalize, and begin a familiar hot history, filled with radiation, then plasma, then the long cooling that eventually allows atoms and galaxies. But some regions fluctuate upward enough to delay the end of inflation, even while their neighbours are already reheating into hot, dense fireballs. Expansion in those regions is so fast that volume grows faster than decay, so the inflating domains do not get used up by the places where inflation ends. The result is self-reproduction, a phrase that sounds biological but refers to space-time geometry and probability. Inflation ends locally yet continues globally, generating an ever-growing inflating background whose total volume increases without bound. Each time inflation ends in a patch, it creates a new reheating region that looks like a Big Bang from the inside, complete with a hot bath of particles and a nearly uniform temperature. In this picture, a Big Bang is a local event, not a universal origin, and the word beginning becomes tied to a boundary in space-time, rather than a single moment everywhere. Our observable universe becomes one reheated region among many, separated from others by distances that inflate faster than light can traverse. The central question shifts from one beginning to many beginnings, and then to what sets the whole process, including the rules that govern which regions end and which continue. To make the mechanism concrete, separate two ingredients that work together, like drift and noise in a physical system. There is classical rolling down a potential, and there is quantum diffusion that sometimes pushes up, and the balance between them determines whether inflation is merely long or genuinely eternal. During each Hubble time, the field changes by a classical amount set by the potential slope, which is the gentle pull of the inflaton's effective force. It also fluctuates by a quantum amount set by the expansion rate, because the de Sitter-like horizon has an associated temperature and a characteristic fluctuation scale. If the quantum step can compete with the classical step, the field performs a random walk, wandering rather than simply sliding. Some patches wander to higher potential energy and inflate longer, and because higher potential energy typically means a larger Hubble rate, those patches also expand more rapidly. Longer inflation means more exponential expansion, which creates more independent Hubble patches, each causally separated by its own horizon. Those patches repeat the same competition between drift and fluctuation, so the process becomes statistically self-sustaining even if any given world line eventually exits. Eternal inflation is therefore not eternal because time runs forever everywhere, as if every region were trapped in endless expansion. It is eternal because the inflating volume never disappears, even as many regions exit, so the global spacetime keeps producing new reheating domains. This is the multiverse idea in its most conservative form, grounded in the dynamics of inflation rather than in speculation about unlimited possibilities. It is not a claim that anything imaginable exists, but that inflation generically produces many causally disconnected domains, each with its own hot beginning and its own subsequent cosmic history. The domains are often described as bubble universes, though the details depend on the inflation model and on how inflation ends. The key point is that reheating surfaces partition spacetime into separate hot regions, and those regions are typically so far apart that no signal can ever pass between them. One common realization uses false vacuum inflation, an idea sharpened in the early 1980s as physicists explored phase transitions in the young universe. The inflaton sits in a metastable high-energy state that decays by quantum tunneling, much like a particle escaping a potential well even when it lacks the classical energy to climb out. Tunneling creates a bubble of lower energy vacuum inside the higher energy background, and the bubble is born at microscopic size before rapidly growing. The bubble wall expands near light speed, while the exterior keeps inflating, so the surrounding false vacuum stretches away and prevents bubbles from easily percolating and ending inflation everywhere. Inside the bubble, vacuum energy is lower, and the field can roll toward a minimum, releasing energy as it settles. That rolling ends in reheating, producing radiation and matter like a hot Big Bang, and from within the bubble the geometry often resembles an open universe with a vast interior. Outside the bubble, the false vacuum still dominates and continues to inflate, like an ocean whose surface keeps rising even as pockets of foam appear. More bubbles nucleate, but the inflating background expands so quickly that it persists, and the global picture becomes a branching structure of births embedded in ongoing expansion. Another realization uses slow-roll eternal inflation without a long-lived false vacuum, relying instead on an exceptionally flat potential. Quantum diffusion keeps some patches high on a flat potential, so inflation never ends everywhere, and the eternal aspect comes from the continual creation of new regions that remain on the plateau. Either way, the global geometry becomes a mosaic of inflating regions and reheated regions, stitched together by causal horizons and expanding boundaries. The reheated regions are separated by distances that grow faster than signals can cross, so even in principle, their histories cannot be compared by direct observation. This is where the multiverse becomes more than a dramatic word, because it changes what we mean by the laws of physics in practice. Different bubbles can inherit different low-energy physics, even if the underlying theory is the same, because the route from high-energy fields to low-energy particles can branch. The reason is symmetry breaking and vacuum selection, familiar from condensed matter and particle physics alike. High-energy fields can settle into different minima, producing different particle spectra and effective constants, and once a region cools into a particular vacuum, it can remain there for cosmic times. In particle physics language, the vacuum is not empty space, but a configuration of fields with definite expectation values. Different vacua can yield different masses, couplings, and even different numbers of light fields, which in turn reshape chemistry, nuclear reactions, and the long-term evolution of stars. String theory amplifies this possibility through the landscape idea, developed as researchers realized how many consistent compactifications might exist. Extra dimensions can be compactified in many ways, producing many metastable vacua with different low-energy properties, and the differences can be discrete rather than continuous. Fluxes, branes, and moduli stabilization can generate an enormous discretion of vacuum energies, each corresponding to a distinct effective four-dimensional universe. The numbers often quoted are staggering, yet the underlying point is simple. There may be many ways to hide extra dimensions while leaving different physics in the large dimensions. Eternal inflation supplies a population mechanism for the landscape, turning a catalogue of possibilities into a cosmological process that explores them. If many vacua exist, inflation can sample them by bubble nucleation and subsequent transitions, and the multiverse becomes a dynamical outcome rather than a mere list. Then the fine-tuning problem is reframed rather than solved, shifting the style of explanation from unique prediction to statistical selection. Instead of one universe with puzzling parameters, there is an ensemble where parameters vary across regions, and we must ask why we find ourselves in this particular subset. The cosmological constant becomes the flagship example, because it is both tiny and consequential for cosmic structure. Its observed value is small compared to naive quantum estimates, yet not exactly zero, and that combination has long tempted physicists to suspect that something deeper is at work. In a landscape, vacuum energy can take many values, and most are too large for galaxies to form before accelerated expansion tears matter apart. Selection effects then become relevant, because observers require long-lived structure, and long-lived structure requires a delicate balance between expansion and gravitational collapse. This is the anthropic argument in its careful form, stripped of slogans and framed as conditional reasoning. It does not claim the universe is designed, but that conditional probabilities differ from raw probabilities, and that what we observe is filtered by the requirement that observers exist to observe it. We must say what has been conditioned on, because vague conditioning turns explanation into hand-waving. We condition on the existence of complex chemistry, stable stars, and enough time for information processing systems to arise, which is a plain language way of saying we condition on robust, long-lived, non-equilibrium complexity. Selection effects can also be applied to the amplitude of primordial fluctuations and other parameters that control structure formation. Too large and structure collapses early into dense objects. Too small and structure never forms, and in either extreme the universe may lack the stable environments needed for slow evolutionary processes. The appeal is that some apparent coincidences become typical within the subset of habitable bubbles, making our observations less mysterious in that restricted ensemble. The cost is that explanation shifts towards statistics over unobservable regions, and that shift forces cosmology to confront how probabilities should be defined. That cost is not only philosophical, because it becomes a technical crisis when the multiverse is infinite. Eternal inflation generically produces infinite volume, and with infinite volume come infinite numbers of events, observers, and even rare fluctuations. If there are infinitely many bubbles of each type, naive counting gives infinity over infinity, which is not a number. Probabilities become undefined without a rule for regulating the infinities, and different rules can yield different answers even when they feel equally reasonable. This is the measure problem, and it is one of the sharpest points where cosmology meets the foundations of probability. It asks how to assign probabilities to outcomes in an eternally inflating space-time, where more volume is constantly being created, and where no natural endpoint exists. In ordinary physics, probabilities are defined by repeated trials, by frequencies in a laboratory, or by a normalized quantum state. In cosmology, there is one universe, and potentially infinitely many regions, so the familiar intuition of sampling breaks down, and must be replaced by a prescription. A measure is a prescription for comparing numbers of events or observers across the multiverse, and it must specify what counts as an event and how to weight it. Different measures are not small tweaks, because they can change predictions, and some measures can even make ordinary outcomes exponentially unlikely. One approach uses a time cutoff, which is conceptually straightforward but physically treacherous. Count events before a chosen global time, then take the cutoff to infinity, and hope the ratio converges, while recognizing that the convergence can depend on the chosen time coordinate. But global time is not unique in general relativity, where many slicings of spacetime are mathematically valid. Different slicings of spacetime can yield different event counts, so the result can be gauge-dependent, and what looks like a prediction can become an artifact of bookkeeping. Another approach uses a scale factor cutoff or light cone time, trying to anchor the cutoff to local expansion history. These try to tie the cutoff to quantities that track physical growth rather than an arbitrary coordinate, yet they still require careful definitions and still face edge cases where intuition fails. There are also local measures, which replace global counting with the perspective of a single world line. Follow a single world line and count what happens in its causal patch, avoiding global infinities at the price of possible bias, because one world line may not fairly represent the full variety of the multiverse. Each proposal aims to restore predictivity, which is the practical goal of any physical theory. Each also introduces its own paradoxes, revealing how strange infinity becomes when combined with exponential expansion, and how sensitive typical outcomes can be to the chosen regulator. The youngness problem is one famous example, and it arises from the simple fact that inflating volume grows rapidly. Some measures predict that most observers should live in very young universes, because volume grows so fast at late times that newly formed regions dominate the count. That prediction clashes with what we observe, since our universe is billions of years old and shows a long, coherent astrophysical history. Fixing the youngness problem often breaks something else, which is a warning that the measure is not a minor technicality but part of the theory's content. Another paradox is the problem of typicality, which becomes unavoidable when there are infinitely many copies of finite histories. In an infinite multiverse, there can be countless copies of any finite observer history, including copies that match your memories up to this very sentence. Then the question becomes which copy you should expect to be, and what you even means in a theory with duplicates. Typicality assumptions become part of the theory, even though they are not directly measurable, and different assumptions can lead to different conclusions about what we should predict next. Boltzmann brains sharpen the issue into a concrete absurdity, using a concept with roots in 19th century statistical mechanics. In de Sitter-like vacua, rare thermal or quantum fluctuations can produce self-aware observers, briefly assembled from random excitations rather than from a long evolutionary history. If the multiverse lasts long enough, Boltzmann brains can outnumber ordinary observers by enormous factors, because even tiny probabilities become significant over infinite time and volume. Some measures then predict we should be such observers, with disordered surroundings and unreliable memories, which is not what we experience. We are not, because our observations show a coherent external world with a long cosmic history, consistent physical laws, and stable records. Any viable multiverse framework must avoid Boltzmann brain domination, either by ensuring ordinary observers dominate the measure, or by ensuring the relevant vacua decay before such fluctuations become common. Avoiding it constrains vacuum lifetimes, decay rates, and measure choices, tying abstract probability questions to concrete model parameters. It also exposes how cosmology forces probability theory into unfamiliar territory, where the difference between rare and dominant can hinge on how infinity is regulated. At this point, the central question returns with new teeth, because multiplying beginnings does not automatically explain the origin of the process. If our Big Bang is one reheating event, what created the inflating background that spawned it, and what fixed the initial conditions that allowed inflation to begin at all? Eternal inflation can postpone a beginning, but it may not remove it, and that distinction matters. The Borde-Guth-Vilenkin theorem suggests inflating spacetimes are past incomplete under broad conditions, meaning that even an eternally inflating future does not guarantee an infinite past. Past incomplete means you cannot extend all geodesics indefinitely into the past, even if the spacetime looks smooth and inflating for a long time. It does not prove a singularity, but it implies inflation alone is not a complete origin story, and it pushes the question back to whatever sets the boundary. So even the multiverse may need a boundary condition, a quantum beginning, or a prior phase that feeds inflation. The earlier chapter's caution about nothing becomes relevant again, because a theory that relies on quantum fields and spacetime geometry is already assuming a rich underlying structure. If we cannot observe other bubbles directly, the multiverse risks becoming untestable. The scientific question becomes whether eternal inflation leaves any observable traces, subtle fingerprints in the sky that survive the thermalization and expansion of our own bubble. There are proposed signatures, and they guide searches even when the odds are uncertain. None are confirmed, and each is contested, but they define what testing could mean, and they clarify which aspects of the multiverse picture are physical hypotheses rather than metaphors. Start with bubble collisions, the most cinematic possibility, and also one of the most straightforward to imagine geometrically. If another bubble nucleated close enough to ours in the past, their walls could have collided, sending a disturbance through the reheating surface and into the primordial plasma. A collision could leave a disk-like feature in the cosmic microwave background temperature map, because the perturbation would affect a circular region on the last scattering surface. It could also produce specific polarization patterns or non-Gaussian correlations, since the collision is a coherent event rather than a random phase fluctuation. Visually, the CMB becomes a mottled sphere of faint hot and cold spots, like a weather map drawn on the inside of a cosmic dome. A collision signature would appear as a subtle bruise, an almost circular imprint whose edge is not perfectly sharp, and whose statistical properties differ from the surrounding fluctuations. Searchers have looked for circular anomalies and matched patterns in the CMB using Bayesian templates and frequentist scans. Results so far are consistent with statistical flukes and foreground systematics, including residual galactic emission and the look elsewhere effect that arises when many patterns are tested. Even a null result is informative, because it constrains collision rates and the geometry of the parent vacuum, narrowing the range of viable parameters. But those constraints depend on the measure and the model, because the expected number of collisions is tied to nucleation rates, expansion history, and how we weight observers. Another possible signature is large-scale anomalies, which sit at the edge of what we can measure cleanly. Some CMB features like low multipole alignments and hemispherical asymmetry have been discussed as hints, because they involve correlations on scales comparable to the observable universe. The problem is that anomalies are hard to interpret, both statistically and physically. Cosmic variance is large on the bigger scales, and a posteriori statistics can exaggerate significance, since we notice unusual features precisely because they are unusual. Spatial curvature is a cleaner handle, because it is tied to geometry rather than to pattern recognition. Many eternal inflation scenarios predict that a bubble interior is an open universe with negative curvature, a consequence of the way bubbles form and the hyperbolic slicing of their interiors. Inflation inside the bubble can drive curvature close to zero, but not necessarily exactly, because a finite number of E-folds leaves a residual imprint. Measuring curvature therefore constrains the number of E-folds after nucleation, and it indirectly constrains how typical our bubble would be in a given model. Current data from the CMB and large-scale structure are consistent with near flatness, with curvature constrained to be extremely small. They place tight bounds on curvature, pushing many simple bubble models into corners and encouraging more elaborate scenarios where post-nucleation inflation lasts long enough to erase most geometric memory. Primordial gravitational waves also matter indirectly, because they are tied to the energy scale of inflation and to the dynamics of the inflaton. The energy scale of inflation affects both tensor modes and the quantum diffusion that can enable eternal inflation, since larger Hubble rates typically enhance fluctuations. If future experiments detect tensors at a significant level, some classes of eternal inflation become more plausible, especially those with high-scale potentials. If tensors remain extremely small, other classes gain ground, including models with low-scale inflation or with potentials shaped to suppress diffusion. Large-scale structure surveys can also test non-Gaussianity and features in the power spectrum, extending beyond the CMB to three-dimensional maps of matter. Some multiverse-motivated models predict deviations from simple slow-roll statistics, such as localized features that reflect transitions in the inflaton potential or remnants of bubble dynamics. Yet the hard truth is that most multiverse predictions are not sharp, because too many ingredients remain uncertain. They often depend on unknown potentials, unknown reheating physics, and an unresolved measure, and those uncertainties can be large enough to accommodate many outcomes. So the chapter must distinguish two claims, because they live at different levels of empirical support. Inflation as a mechanism for perturbations is testable and already constrained by precision data, including the spectral index, limits on tensors, and the near Gaussianity of primordial fluctuations. Eternal inflation as a global picture is plausible within many models, but it's harder to confirm because its defining feature lies beyond our horizon. It sits at the edge where cosmology becomes both physics and inference, and where the boundary between prediction and interpretation becomes thin. This is where philosophy enters, but not as decoration or as a retreat from science. It enters because the theory's output is a distribution over domains, and we observe only one domain, so we must decide how evidence updates beliefs when the sample size is fundamentally limited. We must decide what counts as an explanation and whether statistical typicality is satisfying or merely tolerated. Is it enough to show that our parameters are typical among observers, given a multiverse and a measure, or do we demand a dynamical selection principle that fixes parameters uniquely? The answer shapes which research programs feel satisfying, not only which are consistent, and it shapes what kinds of questions we regard as meaningful. When the multiverse is invoked, the central question is not eliminated, but transformed into a question about meta-laws and boundary conditions. The multiverse also changes the meaning of the central question, because it reframes origin as a process rather than a point, Asking what created the Big Bang becomes asking what created the process that creates many Big Bangs, and what determines the statistical distribution of outcomes across that process. If eternal inflation is correct, a beginning may be local and repeated, while the global story is statistical and potentially past-limited. But the demand for testability does not go away, and the pressure to connect the idea to observable consequences remains a defining scientific constraint. So we end with a pivot that keeps momentum, because the next step is not to abandon origins but to approach them differently. If eternal inflation is difficult to test and may still be past incomplete, other ideas try to avoid a beginning differently by altering the meaning of the hot start itself. Instead of spawning many hot starts, they replace the hot start with a transition from a prior phase, changing the boundary conditions of cosmic history. The next chapter turns to bounce cosmologies, where contraction becomes expansion, and where the Big Bang is reinterpreted as a bounce rather than a birth. Now the story pivots from many beginnings to no beginning at all, or at least to a beginning that is replaced by a cycle or a rebound. We follow the models that trade inflation's reproduction for a universe that cycles or rebounds, and we ask what new problems arise when the singular start is removed. We ended with inflation multiplying beginnings, yet still hinting at a past boundary that refuses to disappear. Bounce cosmologies take a different gamble. They replace a first moment with a turnaround, where contraction becomes expansion. Visually, the idea is simple: a curve that falls, bottoms out, and rises again, like a valley carved into space-time itself. But the physics beneath that curve is anything but simple, because it asks whether the Big Bang was a start or a transition. The motivation starts with general relativity's warning sign from earlier chapters, the one we cannot politely ignore. Run the FLRW equations backward and curvature and density blow up, with the scale factor shrinking towards zero in finite time. A singularity is not a place we can visit. It is a signal that the classical description is incomplete. In GR, that incompleteness is not merely philosophical, it is mathematical, because geodesics end and predictability fails. The Hawking, Penrose's singularity theorem sharpen the point, showing that under broad conditions, like positive energy density and causal structure, collapse and focusing become unavoidable. Those theorems do not tell us what happens at the singularity. They tell us our equations stop being trustworthy. A bounce tries to make that incompleteness constructive rather than fatal, by turning the breakdown into a doorway. If new physics becomes important at extreme density, gravity might turn effectively repulsive, at least for a brief interval. The scale factor could stop shrinking, reach a minimum, then grow. The hot Big Bang becomes the aftermath of the bounce, not the start of existence. That repulsion can be misunderstood, so we should be precise about what is meant. It is not anti-gravity in the everyday sense, and it is not a new force added by hand. It is an effective behavior that can emerge when quantum corrections, exotic stress energy, or modified dynamics change how space-time responds to compression. This idea also matches a stubborn human intuition about cycles and rebounds, the sense that endings can fold into beginnings. Many physical systems oscillate when pushed far from equilibrium, because restoring forces or conserved quantities drive them back. But cosmology is not a pendulum in a room. Any cyclic story must survive thermodynamics, quantum fluctuations, and the observed simplicity of the early universe. So the chapter's central claim is narrow but consequential. Quantum gravity changes the high-density regime in a way that could prevent a singularity. In classical GR, energy conditions make focusing inevitable, and geodesics converge toward a crunch. In quantum settings, those conditions can fail, because vacuum energy, negative pressure, or quantum stress fluctuations can violate classical inequalities. Effective corrections can add pressure-like terms that resist further compression. If you could watch the universe contract in a simulation, the visuals would feel counterintuitive. Galaxies would not merely move closer, the very ruler used to measure distance would shrink, and wavelengths of light would blue shift into harder and harder radiation. Near the would-be singularity, the classical picture becomes a blur, an invitation to replace smooth geometry with something more granular. Bounce models come in families, and they differ in what does the rescuing when density becomes extreme. Some modify geometry itself, treating space-time as emergent or discretized at tiny scales. Some add new fields or new dimensions, changing what counts as matter in the early universe. Some keep GR but change the matter content so the universe violates the usual energy conditions safely. First is loop quantum cosmology, a symmetry-reduced application of loop quantum gravity ideas. In LQC, spacetime geometry is quantized with discrete area and volume, so the continuum is an approximation rather than a foundation. The Planck scale is not just a number here, it is the scale where the granularity becomes dynamically important. At densities near the Planck density, the effective Friedmann equation gains a correction that caps the density, often written as a factor like 1 minus rho over rho critical. The plain language meaning is straightforward. As density approaches a maximum, the expansion rate is forced towards zero. Instead of diverging, the energy density hits a ceiling, and the dynamics turn around. The result is a generic bounce in many LQC setups, not an engineered exception for a special trajectory. When the density approaches a critical value, the Hubble rate goes to zero and flips sign, so contraction transitions to expansion without an infinite curvature singularity. The bounce is driven by quantum geometry, not by exotic matter. In the visuals, the scale factor curve looks smooth, yet the underlying mechanism is discrete, like a digital grid pretending to be a continuous line. LQC then faces the same practical question inflation faced in Chapter 5, because avoiding a singularity is not the same as explaining what we see. Can it explain the horizon and flatness problems and the observed perturbations with the right statistical fingerprints? Some LQC scenarios include a natural onset of slow-roll inflation after the bounce, because the scalar field emerges with favourable conditions. The bounce can kick the field into a region of its potential where inflation becomes likely. In that hybrid picture, the bounce replaces the singularity, while inflation still does the smoothing and the stretching of quantum fluctuations. The test then becomes whether pre-bounce physics leaves any trace after inflation, or whether inflation wipes the slate clean. If inflation lasts long enough, it erases memory by pushing pre-bounce correlations beyond the observable horizon. If it is short or absent, the bounce could imprint features that survive into the CMB. Second are ekpyrotic and cyclic models, motivated by higher dimensional theories that became especially influential in the late 1990s and early 2000s. Here the Big Bang is reinterpreted as a collision or interaction between brains in an extra dimension, a modern echo of older cosmic egg intuitions. The visible universe is a three-dimensional brain. The hot phase begins when brains approach, and energy is released into particles. In visual terms, imagine two vast, nearly featureless sheets drifting through a higher dimensional space, with a thin gap between them shrinking. The collision is not like billiard balls. It is more like a boundary condition changing abruptly, converting stored energy into heat and matter on the brain we inhabit. Ekpyrosis is not just a brain story, and in practice many versions can be described in four-dimensional effective field theory. It is a dynamical smoothing mechanism during a slow contraction phase with a very stiff equation of state, meaning pressure greatly exceeds energy density in a specific technical sense. In that phase, anisotropies and curvature dilute relative to the ekpyrotic energy component. The universe becomes flat and homogeneous as it contracts, which is the opposite of what naive collapse would suggest. That sounds like inflation's smoothing, but it runs in the reverse time direction. Inflation smooths by rapid expansion, making curvature and inhomogeneity negligible by stretching them away. Ekpyrosis smooths by slow contraction with W much greater than 1, making the stiff component dominate the energy budget. Both aim to make the observed large-scale order an attractor, not a fine-tuned initial condition. The hard part is the bounce itself, and this is where elegant cartoons meet stubborn equations. Classical GR does not allow a smooth transition from contraction to expansion without violating energy conditions or introducing singular behavior. Ekpyrotic models therefore require a non-singular bounce mechanism, often involving ghost condensates, Galilean-like fields, or other effective theories. These ingredients are chosen because they can violate the null energy condition in a controlled way, at least within the regime where the effective description holds. Cyclic versions repeat this sequence, building a full narrative arc rather than a single event. A dark energy-like phase expands and empties the universe, diluting ordinary matter and radiation until the cosmos looks cold and nearly vacant. Then contraction begins, ekpyrotic smoothing occurs, and a bounce produces a new hot phase. The central promise is dramatic, Our universe could be one cycle in an endless sequence, with no absolute beginning. Third are matter-bounce scenarios, which aim to generate the observed perturbations without inflation, keeping the story closer to familiar cosmic ingredients. In a matter-dominated contraction, vacuum fluctuations can exit the horizon and become nearly scale invariant, because the shrinking horizon behaves differently than in expansion. After the bounce, those modes re-enter and seed structure, mimicking inflation's main success. The pitch is bold. Keep the perturbation triumph, drop the inflationary expansion. Matter bounce models must still control anisotropies, which tend to grow during contraction and can overwhelm the smooth background. This is the BKL instability in practical form, where shear terms scale aggressively and drive chaotic mixmaster behavior. Many matter bounce constructions add an ekpyrotic phase to suppress that instability, or they engineer special matter components with stabilizing properties. The bounce again requires new physics at high density, and the details determine stability. Across all families, the horizon problem is reframed rather than simply solved in the inflationary way. In contraction, regions that are far apart today can have been in causal contact before the bounce, because the co-moving horizon can grow instead of shrink. A long contracting phase can allow thermalization, or at least causal coordination, so temperature and density can homogenize before the turnaround. The observed uniformity becomes a memory of pre-bounce contact. Flatness is also reframed, and the visuals help here, because curvature behaves like a competing energy component. In inflation, curvature is diluted by expansion, rapidly becoming negligible compared with vacuum-like energy. In ekpyrotic contraction, curvature is suppressed relative to the stiff component, because the ekpyrotic energy density grows faster than curvature as the universe contracts. In LQC with post-bounce inflation, flatness is again handled by inflation. Each model claims to make today's near-flat geometry less fragile. Perturbations are the real battleground because they are measured with precision and compared across multiple datasets. Any viable bounce must reproduce the CMB's nearly scale-invariant spectrum, its slight tilt, and its predominantly adiabatic character. It must also keep non-Gaussianity within tight bounds, because higher-order correlations are now constrained, not speculative. It must not generate forbidden isocurvature modes that would show up as mismatched patterns in temperature and polarization. Inflation predicts a specific pattern that has become a benchmark. Nearly Gaussian scalar perturbations with a small tilt, typically red, meaning slightly more power on large scales. A potentially detectable tensor background, depending on the energy scale of inflation and the shape of the potential. Bounce models often predict different combinations, and those differences are the evidence bridge we promised in earlier chapters. Start with tensor modes, the primordial gravitational waves that would leave B-mode polarization in the CMB. In many ekpyrotic models, primordial gravitational waves are strongly suppressed because the contraction phase does not amplify tensors the way inflation does. The background evolution makes it difficult to produce a large, nearly scale-invariant tensor spectrum. That typically implies an extremely small tensor-to-scalar ratio, effectively pushing tensors out of reach. A future detection of sizable primordial B-modes would therefore pressure simple ekpyrotic scenarios, forcing either additional mechanisms or a rethinking of the contraction history. But absence of detection is not a clean win for ekpyrosis, because inflation can also produce small tensors. The real question becomes whether a measured spectrum, if found, matches inflation's consistency relations or violates them. Matter bounce models can produce tensors, but the tensor spectrum and its tilt can differ from inflation in ways that matter observationally. Some versions predict a blue tensor tilt, with more power at small scales, which sounds exciting until constraints arrive. Too much small-scale gravitational wave energy affects the expansion history, tightening bounds from nuclear synthesis. It can also show up in pulsar timing arrays, where stochastic backgrounds alter timing residuals. LQC can also modify tensor propagation near the bounce, and here the details are technical but important. Depending on the effective dynamics, tensors can pick up features, altered phase evolution, or modified consistency relations between scalar and tensor amplitudes, but predictions vary with quantization choices and with how one treats perturbations through the bounce, including matching conditions and gauge subtleties. The theory space is broad, and the observational targets must be chosen carefully. Next is non-Gaussianity, the higher-order statistics of primordial fluctuations, which act like a fingerprint rather than a headline number. Single-field slow-roll inflation predicts very small local-type non-Gaussianity, because interactions are weak and the perturbations are close to free fields. Many bounce mechanisms involve multiple fields or non-trivial interactions near the bounce, where higher derivative terms and mixing can become important. That can generate larger non-Gaussianity, often with distinctive shapes in momentum space. Ekpyrotic models historically struggled here, and the struggle is instructive rather than embarrassing. Converting entropy perturbations into curvature perturbations can produce sizable local non-Gaussianity, because the conversion is nonlinear and sensitive to the trajectory and field space. Model builders have developed mechanisms to suppress it, including smoother conversion or specific potentials, but the constraints from Planck remain a sharp filter. Non-Gaussianity is not decoration, it is a discriminator. Matter bounce scenarios can also generate characteristic bispectrum shapes, and the sign can matter as much as the magnitude. Some predict large non-Gaussianity with specific momentum dependence tied to the bounce dynamics or to non-canonical kinetic terms. Even if the power spectrum looks inflation-like, the three-point function can reveal a different origin. The challenge is to make these predictions robust, not adjustable after the fact. Then there are features in the primordial power spectrum itself, which is where a bounce can leave a more direct scar. A bounce can imprint oscillations, a cutoff, or a localized dip at the larger scales, depending on how modes evolve near the turnaround. These features can arise because modes experience a non-adiabatic evolution near the bounce, or because initial conditions are set in a pre-bounce vacuum that is not the usual bunch, Davis state. In visuals, this becomes a graph where the smooth tilt is interrupted by ripples or a gentle bend. This connects to the CMB anomalies discussed in the Multiverse chapter, the Lowell oddities that tempt interpretation. Lowell power suppression, hemispherical asymmetry, and other large-scale quirks are not decisive evidence, because cosmic variance makes the larger scales statistically noisy, but bounce models sometimes predict large-scale modifications more naturally than simple inflation, precisely because the largest modes are most sensitive to pre-bounce history. The risk is overfitting cosmic variance, mistaking a statistical fluke for a fossil. Large-scale structure surveys extend the test beyond the CMB, turning primordial statistics into late-time patterns. Scale-dependent bias can constrain local-type non-Gaussianity, because it changes how galaxies trace underlying matter on large scales. The distribution of galaxies and the lensing of the CMB can test running and features in the spectrum. Future 21 cm measurements could probe small-scale power where some bounce models differ strongly, potentially revealing excess power or damping that the CMB cannot resolve. Yet bounce cosmology has a deeper internal problem that inflation mostly avoids, and it is not primarily about fitting a spectrum. It is the entropy and memory problem, the question of whether cycles can truly repeat without drifting. If the universe cycles, entropy tends to increase each cycle, because irreversible processes leave a record. More entropy means larger volume or longer cycles, and the past becomes dominated by high entropy states. This is Tolman's old argument in Modern Clothing, dating back to early 20th century debates about oscillating universes. A truly cyclic universe seems to drift, not repeat, because each cycle inherits the thermodynamic cost of the last. Each cycle would be bigger and more dilute, and the notion of an eternal steady rhythm breaks. The question becomes whether the cycle is real, or whether the model is only quasi-cyclic. Ekpyrotic cyclic models propose partial answers, and the proposals are clever enough to deserve careful attention. A long, dark energy-like expansion phase can dilute matter and radiation, effectively resetting conditions before contraction begins, at least within the observable patch. The ekpyrotic phase then smooths and flattens, acting like a cosmic cleaning step that suppresses dangerous anisotropies. But entropy is not destroyed. It is relocated, and critics argue the bookkeeping remains incomplete. Some proposals rely on extra dimensions as an entropy sink, using the brain picture to separate what we observe from what exists. If most entropy is carried off the brain into the bulk, the observable brain could re-emerge relatively clean each cycle, with a low entropy effective state. That idea depends on detailed higher dimensional dynamics that are not yet derived from a complete theory. It also raises the question of what counts as the universe when entropy leaves our sector. Other proposals focus on selecting a low entropy slice at the bounce, using quantum cosmology ideas that treat the bounce as a special kind of boundary. But that returns us to Chapter 4's tension, where a boundary condition can be a rule yet still function as fine-tuning. If the bounce requires special quantum initial conditions, have we really replaced the beginning or just renamed it? The discomfort is not aesthetic. It is about explanatory depth. Memory is also a perturbation problem, not only a thermodynamic one, because contraction can amplify the wrong kinds of structure. In contraction, anisotropies and inhomogeneities can grow and dominate, threatening a chaotic mixmaster approach where different directions expand and contract unpredictably. Ekpyrotic smoothing is designed to suppress that, but it must win against generic perturbations and against the sensitivity of the bounce mechanism itself. Stability is not optional. It is the difference between a controlled bounce and a crunch. There is also the question of what survives the bounce in any model, which is partly technical and partly conceptual. Do correlations pass through, or are they scrambled by strongly curved quantum-dominated dynamics? If information survives, the universe carries a record of a prior phase, and we can hope to detect it in subtle statistics. If information is erased, the bounce becomes observationally indistinguishable from a beginning, even if it is mathematically smooth. This is where the central question sharpens, because it is easy to like the bounce as an idea, and harder to make it a scientific claim. If a bounce happened, it is a claim about a prior physical regime, not just a philosophical comfort. It must imply something measurable now, even if only statistically, because cosmology lives and dies by traces. Otherwise, it risks becoming a story that explains the boundary by moving it into an untestable past. So we ask what would count as evidence of a pre-bounce universe, and we keep the list concrete. A distinctive tensor spectrum that inflation cannot easily mimic, perhaps with a tilt or feature tied to contraction. A specific non-Gaussianity shape that points to multi-field conversion or bounce interactions near the turnaround. A robust large-scale feature that survives later evolution and is not a foreground artifact or a data processing mirage. We also ask what would count as evidence against a bounce, because good theories accept the possibility of failure. A clean detection of inflationary consistency relations linking tensors and scalars would favour simple inflation, tightening the room for alternatives. Strong limits on non-Gaussianity and on power spectrum features squeeze many bounce constructions, especially those that rely on strong interactions. A continued absence of any bounce-specific signature does not kill the idea, but it narrows it. At the same time, bounce models remind us that singularity avoidance is not the same as explanation, and this distinction is easy to miss in popular summaries. Removing the singularity can be a mathematical repair, a way of keeping equations finite. It can also be a physical claim about quantum gravity, telling us what space-time is made of at the smallest scales. The difference depends on whether the bounce mechanism is derived from a deeper theory, and whether it makes sharp predictions. Loop quantum cosmology offers a concrete effective equation, but it inherits ambiguities from quantization choices, factor ordering, and how one defines geometric operators. Ekpyrotic models offer a smoothing attractor, but they require careful control of the bounce and of perturbation conversion from entropy to curvature. Matter bounce scenarios can mimic scale invariance, but they fight anisotropy and stability constraints that are unforgiving. Each approach buys one advantage and pays for it elsewhere. The documentary stakes rise here because the bounce option changes what before means, and it changes it in a way audiences can feel. In inflation and multiverse stories, the Big Bang is a local event in a larger expanding background, and before can mean elsewhere. In bounce stories, the Big Bang is a transition surface, and the prior phase is our own universe's history, not someone else's bubble. The camera is no longer panning across a landscape. It is turning back along our own timeline. That shift makes the arrow of time unavoidable, because a contracting phase forces the question into the open. If the universe contracted, why does time feel like it flows from the bounce outward rather than inward? Why do we remember the past and not the future, even if the equations are time-symmetric in many regimes? Why is entropy low near the bounce, if the bounce is not a special beginning? In a cyclic picture, why doesn't the universe look old in every direction? Some bounce models suggest the arrow of time could reverse across the bounce, with two time directions emerging from a low entropy minimum, like a symmetric hourglass. Others treat the bounce as a special boundary condition that sets the arrow, making the bounce a kind of temporal origin, even if it is not a geometric singularity. Either way, the bounce does not remove the time problem, it exposes it. Now the story pivots from geometry to temporality. If a bounce replaces the beginning, we still must explain why history has a direction. The next chapter follows that deeper question, asking what sets the arrow of time in any universe that can begin or rebound. We ended at the bounce and met a sharper problem than singularities, because any origin story must also explain why time has a direction. In the visuals, the universe is no longer a simple timeline. It becomes a landscape of possible histories, with one path lit and the others dim. Physics at the microscopic level is mostly time reversible, meaning that many fundamental equations work almost as well backward as forward. If you filmed two particles scattering in a vacuum and played it in reverse, the motion could still satisfy the same laws. Yet our experience is not reversible, because records form and decay, and because memory itself depends on irreversible physical processes. A footprint in wet sand dries and crumbles, a photograph fades, and a hard drive slowly accumulates errors from radiation and heat. Those are not just poetic examples, because they are physical records that require energy dissipation to create and preserve. The arrow we live inside is the arrow of reliable records, an arrow that points towards states where information about the past becomes harder to maintain. The everyday arrow is thermodynamic, and it is the one we can measure with thermometers, engines, and chemical reactions. Entropy tends to increase, so the macroscopic future is the direction of higher entropy, where energy is more spread out and less able to do useful work. In a cinematic sense, the future is where gradients flatten, hot and cold mix, pressure differences equalize, and organized motion turns into heat. This is not a mystical force pushing clocks forward, and it does not require new laws of nature. It is a statistical statement about many particle systems and typical behavior, because there are overwhelmingly more ways to be messy than to be neat. When we say entropy increases, we are really saying that a system is vastly more likely to wander into one of the many disordered arrangements. A broken cup does not reassemble, because there are vastly more disordered microstates than ordered ones, and the probabilities are lopsided. The shards can lie in countless orientations with tiny variations in position and vibration, while the intact cup occupies an astronomically smaller region of phase space. Even if the microscopic laws permit reversal, the required coordination is so extreme that it is effectively never realized. So the central question returns in a new form. If the Big Bang is the earliest known state, why was it so special thermodynamically? The documentary's camera can linger on that phrase because it reframes the mystery from what happened to why was the beginning so unlikely. At first glance, the early universe looks like the opposite of low entropy, because it was hot, dense, and filled with radiation. It resembles a furnace glowing in every direction, with particles colliding constantly, and energy packed into a tiny volume. If we only think in terms of gases in a box, hot and well mixed usually sounds like high entropy. Hot does not automatically mean high entropy for the whole universe, and the typo itself almost helps, because it reminds us how easy it is to misread the clue. The key is that gravity changes what counts as order, and gravity is not a small correction in cosmology. On the larger scales, gravity is the stage, the script, and the lighting. In non-gravitating systems, uniformity is bland and high entropy, because the particles have explored their available space and spread out evenly. A gas that fills a room is done, in a thermodynamic sense, since there are few macroscopic gradients left to exploit. But in gravitating systems, uniformity is rare and low gravitational entropy, because gravity makes clumping the more probable and more information-rich outcome. Gravity prefers clumping, because clumps can deepen potential wells and open more ways to arrange matter, while also allowing energy to be released as heat and radiation. A smooth mass distribution is constrained, almost like balancing a pencil on its tip across the entire cosmos. Small inhomogeneities tend to grow, because slightly denser regions pull in more matter and become denser still. The early cosmos was nearly homogeneous, with fluctuations at only 1 part in 100,000, and we can see that directly in the cosmic microwave background. On screen, the CMB map looks like a soft, mottled sphere. Tiny, warm and cool speckles on an otherwise uniform glow. That smoothness is a kind of order, and it is precisely the kind that gravity finds unnatural. As the universe expands and structures form, entropy rises in multiple channels at once, and they reinforce each other. Gas collapses into galaxies, shocks heat interstellar matter, stars ignite, and nuclear fusion converts low-entropy fuel into higher-entropy radiation. Meanwhile, gravitational degrees of freedom proliferate, because the geometry becomes more complex and the distribution of mass becomes more intricate. Black holes are the extreme case, and they are not just dramatic objects but thermodynamic ones. They carry enormous entropy, so a universe with many black holes is far more entropic than a smooth one, even if its average temperature is lower. The Bekenstein-Hawking formula ties entropy to horizon area, turning a geometric surface into a count of hidden microstates. That connection is one of the great conceptual shifts of 20th century physics, because it tells us that space-time itself has thermodynamic bookkeeping. When matter collapses past an event horizon, the information accessible to the outside world shrinks, and the entropy assigned to the horizon grows. In the late universe, the entropy budget is dominated not by starlight or gas, but by the quiet, enormous accounting of black hole horizons. This reframes the puzzle, and it makes the early universe look stranger, not simpler. The Big Bang was hot, but it was also astonishingly smooth, and that combination implies low total entropy when gravity is included. The beginning was not maximally random in the gravitational sense, it was delicately arranged. Roger Penrose sharpened this into an argument about improbability, and he did it with the instincts of a geometer. If you pick initial gravitational conditions at random, smoothness is fantastically unlikely, because most geometries are wrinkled with tidal distortions and gravitational radiation. His point is not that we can literally roll cosmic dice, but that generic initial data would not resemble what we infer. Penrose estimates the phase space fraction for such a low entropy gravitational state is absurdly tiny, and the number is so small it functions as a warning. It is the kind of number that makes the narrator pause, because it suggests that something is being selected, not merely happening. When improbability becomes that extreme, it stops feeling like chance and starts feeling like a boundary rule. The warning is not about arithmetic, and it is not a rhetorical trick. It is about explanatory burden, because a beginning that's special looks like a boundary condition, not an outcome of ordinary evolution. If the arrow of time is entropy increase, then the arrow seems to be set by the initial condition, and the beginning chose the direction. Penrose proposed a way to formalize that specialness, because physics prefers quantities you can calculate. His Weyl curvature hypothesis says the Weyl tensor should vanish or be minimal at the initial boundary, in contrast with generic gravitational data. It is a proposal that turns smoothness into a precise geometric constraint. Weyl curvature tracks tidal distortions and gravitational radiation, the parts of curvature not fixed directly by local matter density. Low Weyl curvature corresponds to a smooth geometry with little free gravitational clumping, like a calm sea before waves have formed. High Weyl curvature, by contrast, corresponds to a space-time full of shear, distortion, and gravitational degrees of freedom. In this view, the Big Bang is not just hot, and it is not just dense. It is geometrically constrained in a way that suppresses gravitational entropy, leaving the universe with room to develop structure later. The arrow then becomes a story of geometry unfolding, smooth initial conditions giving way to an increasingly corrugated cosmos. The hypothesis is attractive because it connects a vague idea to a geometric quantity, and it gives the puzzle a mathematical handle. But it also raises a deeper question about why that constraint holds, and whether it is fundamental or emergent. If we accept a special boundary, we still have not explained it, because we have only named the rule the beginning seems to obey. This is where inflation re-enters the story, because inflation was built to explain large-scale smoothness in the first place. It stretches a small patch into a uniform cosmos, and it does so with exponential expansion that can erase many initial irregularities. Visually, the universe becomes a tiny bubble that swells so fast that any wrinkles are pulled nearly flat. Inflation can make the observable universe look homogeneous and flat, and it can also seed the tiny perturbations we measure in the CMB. Quantum fluctuations in the inflaton field get stretched to cosmic scales, becoming the seeds of galaxies and clusters. The same mechanism that smooths also imprints a delicate pattern, nearly scale invariant, slightly tilted, and overwhelmingly Gaussian. But the entropy question is subtle, because inflation smooths and dilutes, yet it does not automatically explain why the inflating patch existed. To start inflation, you need a region dominated by vacuum-like energy with the right field configuration, and that region must already be smooth over a Hubble scale. In other words, inflation can amplify a favourable start, but it may not manufacture that favourability from nothing. Inflation can turn moderate smoothness into extreme smoothness, and that is a genuine explanatory gain. It may not explain the low-entropy gravitational state that allowed inflation to begin, at least not without additional assumptions about what initial states are typical. The camera can show a small calm patch inside a larger storm, and the question becomes why that calm patch existed at all. Some argue inflation helps because it creates a huge volume of reheated, high-entropy radiation, and that is not a trivial point. Reheating produces many particles and many microstates, filling the universe with a thermal bath that later cools into the CMB. In that phase, entropy density is high, and the number of accessible matter configurations is enormous. Yet the arrow problem is about the whole history, not only about reheating, and not only about matter. A high-entropy end state does not explain a low-entropy start, because the arrow is defined by the gradient from special to typical. If the beginning is already typical, the arrow loses its anchor, and the story becomes circular. In many models, inflation itself resembles de Sitter space, which has a horizon and an associated entropy. That entropy is large, but it is not the same as matter entropy, and it behaves differently under coarse graining. De Sitter entropy counts horizon degrees of freedom in a way that is still debated, and it complicates any simple slogan about inflation increases entropy. So we must ask what entropy we are counting, because gravity forces us to separate categories that are usually merged. Gravitational entropy, horizon entropy, and coarse-grained matter entropy do not always align, and they can even move in different directions during different phases. The narrator can linger on that ambiguity, because it is where intuition often fails. This is why critics say inflation may shift the problem, rather than solve it, by trading one special condition for another. It can explain why our patch is smooth, while assuming a special pre-inflationary condition that is smooth enough to ignite. Supporters respond that inflation makes smoothness an attractor, because expansion can wash out many irregularities even if the initial state is not perfectly tuned. The dispute becomes technical and conceptual, and it is not settled by a single calculation. How generic are inflationary initial conditions in a full theory, and what measure defines generic, especially when spacetime itself is dynamical? If you cannot define typicality, you cannot say what inflation explains, and the argument becomes about what counts as a fair comparison. The measure problem from the Multiverse chapter returns here in a new disguise, because eternal inflation magnifies it. If inflation can continue in some regions, producing a multiverse of pocket universes, then most becomes a dangerous word. Without a principled measure, probabilities can be regulator-dependent, and explanations can become artifacts of bookkeeping. Quantum cosmology also returns, because boundary proposals can select low-entropy states without invoking a prior time. Hartle-Hawking and Vilenkin differ on weighting histories, but both treat the beginning as a quantum boundary rather than a classical event. In these approaches, the universe is described by a wave function over geometries, and the question becomes which geometries are favoured. A boundary condition can set the arrow without a prior time, and that is both elegant and unsettling. The word cause becomes slippery because causes normally sit inside time, with earlier events producing later ones. Here, the cause is more like a selection rule, and the selection rule is written at the edge of what time even means. This is the point where the documentary's hook becomes unavoidable, because language starts to strain. Before the first second, the usual meaning of before may fail, and the visuals can reflect that, with clocks dissolving into geometry. The narration can slow, because the question is not merely unanswered, but partially ill-posed. Some proposals embrace that failure and redefine the question, which is a move science sometimes has to make. Instead of asking what happened before, they ask what boundary condition replaces before, and what symmetry or principle fixes it. The mystery shifts from chronology to consistency. One family of ideas is two-headed time, and it takes the low-entropy boundary seriously as the central feature. The universe has a special low-entropy boundary, and entropy increases away from it in both directions, like heat flowing outward from a coldest point. In that picture, the boundary is like a temporal equator, and observers on either side call their direction away from it the future. The laws remain time-symmetric, but the solutions are not, and that distinction matters. The arrow emerges because the boundary is special, not because dynamics prefer one direction, and that preserves microscopic reversibility. It also suggests that what we call past is simply the direction toward lower entropy, not a metaphysical category. This can be applied to bounce scenarios, where contraction leads to a minimum and then expansion resumes. The bounce could be the low entropy minimum, with two expanding branches and opposite arrows, each branch experiencing itself as moving away from the special surface. The symmetry is visually striking. Two universes back to back, sharing a boundary but not a common future. It can also be applied to quantum origin stories, where a no boundary or tunneling condition could define a minimal entropy surface from which time emerges. In those pictures, time is not a pre-existing container. It is a coordinate that becomes meaningful only when the universe has a thermodynamic gradient. The arrow is then not added to the universe, but extracted from its boundary data. A related modern idea is CPT symmetric cosmology, and it uses a symmetry that is deeply embedded in quantum field theory. It proposes the universe is symmetric under charge, parity, and time reversal across the Big Bang, so the full history respects CPT even if each branch looks asymmetric. In some versions, the Big Bang is not a singular start but a symmetry surface, and the pre-Big Bang branch is the CPT mirror of our branch. The appeal is that it makes the beginning less arbitrary, because symmetry can play the role of a law. The boundary is fixed by symmetry, and the arrow can be defined consistently on both sides, with antimatter and handedness reversed in the mirror branch. But the cost is interpretive, because we must ask what before means if time points away from the boundary in both directions. For an observer in our branch, the other branch is not earlier in our time, and it is not part of our causal past. It is earlier only in a coordinate that does not match our thermodynamic arrow, which is the only arrow our brains and instruments can follow. That matters because it changes what counts as an explanation and what counts as a prediction. A symmetric extension can remove a hard edge, while still requiring a special low-entropy surface, and that is the trade. Even in a two-headed model, the low-entropy boundary is doing the work, and the question becomes why that boundary is low entropy at all. Penrose would say symmetry is not enough, because a generic symmetric boundary could still have high Weyl curvature, so the improbability remains. Supporters answer that quantum gravity may restrict allowed boundary data, and that classical intuition about generic may be misleading. The space of possible beginnings might be smaller than we imagine, because not every classical geometry corresponds to a consistent quantum state. That is a promise, not yet a derivation, and without a complete quantum gravity theory, we cannot compute the true distribution of initial geometries. This is why the arrow of time is not a side issue, and why it belongs in a documentary about origins. It is a filter that origin stories must pass, because it ties mathematics to what we experience, from broken cups to the formation of memories. If the beginning is low entropy by fiat, we risk replacing explanation with stipulation, and if the beginning is generic, we must show how the arrow still emerges. The stakes rise because the arrow is also a constraint on multiverse reasoning, and it forces uncomfortable comparisons. If most regions are high entropy, why are we not Boltzmann brains, brief observers fluctuating out of equilibrium with false memories? A universe that lasts forever in a de Sitter-like state can produce rare observers by fluctuation, and avoiding that outcome links cosmology to thermodynamics. So the arrow problem connects chapters that seemed separate, and it does so with surprising force. It links inflation's initial conditions, the bounce's time reversal, and the multiverse's measures, because each framework must say what is typical and why. The arrow is the thread that ties abstract probability to lived experience. Now we return to the central question with a sharper edge, because we can state it without metaphor. If the Big Bang set the arrow, then what set the Big Bang's low entropy rule? There are several possible answers, and each has a different meaning of before, which is why the debate is partly scientific and partly conceptual. One says the beginning is a boundary law, not an event, and the arrow is encoded in that law. Another says the beginning is a transition, but the arrow flips across it, so each side experiences its own future. Another says inflation makes order typical within a larger ensemble, but only after we choose a measure that makes typical well-defined. Each answer makes different bets about observables, and that is where philosophy becomes physics again. If the arrow is tied to Weyl curvature, we should look for traces of primordial gravitational degrees of freedom, especially in the form of relic gravitational radiation. If inflation is the key, we should look for the specific patterns inflation predicts, because those patterns are the fossil record of the earliest dynamics. The spectral tilt, non-Gaussianity limits, and tensor modes become arrow evidence, because they constrain what the early universe was allowed to be. A slightly red tilt supports slow roll dynamics, while strong non-Gaussianity would point to more complex fields or interactions. Tensor modes, if detected, would indicate a high energy scale and a particular kind of early time quantum fluctuation. If a two-headed or CPT symmetric boundary is real, it might imply distinctive neutrino physics, or specific correlations at the larger scales, and those are not casual add-ons. It might also predict suppressed primordial tensors, depending on how the symmetry constrains initial perturbations. These are not guaranteed signatures, but they are the kinds of handles that turn a metaphysical question into a research program. We should also be honest about what cannot be tested directly, because honesty is part of the scientific tone. We cannot observe the other time branch if it is causally disconnected by definition, and we cannot replay the beginning like an experiment, but we can test whether our branch looks like it emerged from a special low-Weyl boundary, and we can test whether initial perturbations match simple vacuum assumptions. We can test whether inflation smoothing is enough, or whether anomalies persist that suggest pre-inflationary structure, and we can test whether curvature is exactly zero or merely small. Each of those tests is indirect, but indirect does not mean weak, because cosmology often advances by ruling out broad classes of histories. The sky's a dataset, and it carries constraints that no laboratory can replicate. Future CMB polarization experiments tighten the net, because polarization is where primordial gravitational waves would leave their cleanest imprint. They can push limits on primordial B modes, constrain isocurvature, and improve non-Gaussianity bounds, all while controlling foregrounds from dust and synchrotron emission. On screen, the polarization map becomes a delicate pattern of curls and gradients, and the question is whether any of those curls are primordial. Large-scale structure surveys add different leverage, because galaxies trace the growth of initial perturbations into the cosmic web. They probe scale-dependent bias, primordial features, and the growth history that connects initial conditions to today, including subtle signatures in baryon acoustic oscillations. Visually, the universe becomes a network of filaments and voids, and the narration can remind us that this web grew from tiny CMB speckles. Gravitational wave observatories extend the search beyond the CMB, because the early universe could have produced backgrounds at frequencies the microwave sky cannot access. A stochastic background across frequencies could reveal early universe phases, including reheating details or alternative pre-Big Bang dynamics, even if the CMB looks smooth. The soundscape of spacetime becomes another channel of evidence, translating curvature into measurable strain. If we find a tensor spectrum consistent with simple, slow-roll inflation, many bounce and two-headed scenarios will be squeezed because they must reproduce that specific signature. If we find no tensors and strong limits, high-scale inflation and some eternal models weaken, and attention shifts to lower-scale or more intricate mechanisms. Either outcome is informative because it narrows the space of viable beginnings. If we find specific non-Gaussian shapes, multi-field bounces and exotic reheating histories gain plausibility because they naturally generate correlations beyond the simplest vacuum fluctuations. If we find a perfectly featureless spectrum, many alternatives lose room, and simplicity wins by surviving. The arrow of time therefore becomes a practical guide, because it tells us which questions are about taste and which are about measurable consequences. We can now state the chapter's conclusion in plain terms, without losing the scientific edge. The early universe was not just hot, it was extraordinarily ordered in the gravitational sense, and that order is what made room for an arrow. That order is what makes time feel like it flows, because it created a vast entropy gradient that the universe has been climbing ever since. Any story about what created the Big Bang must explain why entropy started so low, especially in the gravitational sector where order means smoothness. The beginning was not merely a high-energy state, but a geometrically special one, and that specialness is the real clue. To move beyond speculation, we need to ask what future observations could actually arbitrate between these origin stories. The next chapter turns from principles to tests. We have chased the Big Bang to a boundary where time and geometry blur, and where familiar cause and effect becomes a careful approximation. Now the question becomes operational, because physics advances by asking what could be measured. What messages could survive from the first instance, or from whatever came before, and still be legible after 13.8 billion years of expansion? Cosmology is not a time machine, but it is a forensic science, built on conserved quantities and statistical traces. The early universe wrote patterns into radiation, matter, and space-time itself. Then it diluted and stretched them across the sky. Our job is to read those patterns without inventing them, and to separate primordial ink from later smudges. The cleanest fossil is the cosmic microwave background, because it is a calibrated snapshot of a specific epoch. When the universe cooled enough for electrons and protons to form neutral hydrogen, photons stopped scattering freely and began streaming. That last scattering surface is not a wall, but a thin shell in time. Still, it is our sharpest image of the early plasma. The CMB carries temperature anisotropies at the 10 to the -5 level, tiny ripples on a nearly uniform 2.7 Kelvin glow. In visuals, it is a mottled sphere, with warm and cool patches that look like weather but encode primordial statistics. It also carries polarization, a faint directional preference in the photon electric field, which is where the earliest dynamics can hide. Polarization is generated because Thomson's scattering cares about geometry, and it imprints a pattern when the incoming radiation has a quadrupole anisotropy. That is a technical statement with a simple meaning. The plasma must see the sky as slightly lopsided. Once produced, the polarization field can be decomposed mathematically into two families, called E modes and B modes. E modes are gradient-like patterns sourced mainly by density perturbations, and they align into radial and tangential motifs around hot and cold spots. B modes are curl-like patterns that require something that can twist the polarization field, producing a pinwheel signature. In maps, that twist looks subtle, but its origin would be profound. Primordial gravitational waves are the classic source of large-scale B modes, and the logic is beautifully direct. They are tensor perturbations in the metric, not waves moving through space like sound through air. A passing tensor mode shears space-time itself, so the plasma's scattering geometry is distorted, and the polarization is rotated into a curl component. If inflation happened at high energy, it generically excites these tensor modes from quantum fluctuations, then stretches them to cosmic scales. The historical arc matters here, because inflation was proposed to solve horizon and flatness puzzles, and the tensor prediction became its most romantic test. The same quantum mechanics that seeds density ripples would also shake the fabric of space-time, leaving a polarization whisper. That link is summarized by the tensor-to-scalar ratio, R, which compares tensor power to scalar power at a reference scale. Scalars seed structure and dominate the temperature map, so they are already measured with exquisite precision. Tensors would add a distinct B-mode signal at degree scales, with an amplitude directly tied to the inflationary energy scale. So R is not just a parameter, because it functions like a lever that lifts entire classes of early universe models. A detection at R around 10 to the -2 would favour high-scale, slow-roll inflation and pressure many bounce scenarios. It would also imply an inflationary energy density near grand unification scales, linking the sky to particle physics ideas that were once purely theoretical. A continued non-detection also speaks loudly, because absence can be a measurement when sensitivity is high. It pushes inflation toward lower energy scales and flatter potentials, where tensors are naturally suppressed. It also makes some alternatives harder to distinguish, because many models can hide tensors below current limits, while still matching the scalar spectrum. But B modes are not a single clean channel, and the sky does not label its contributions. Gravitational lensing converts some E modes into B modes as photons pass through the cosmic web of galaxies and dark matter. That lensing B mode is a known contaminant, yet it is also a signal of structure growth, so it must be modelled, reconstructed, and subtracted with care. The harder problem is foregrounds, especially polarized dust and synchrotron emission, because they are bright and spatially complex. Dust grains align with magnetic fields and emit polarized light, tracing the Milky Way's magnetized interstellar medium. Synchrotron radiation comes from relativistic electrons spiraling in magnetic fields, and it is strongly polarized at low frequencies. That polarized emission can mimic primordial B modes if frequency coverage is too narrow, or if spatial templates are overtrusted. In visuals, the danger is striking. A beautiful, swirling pattern that looks cosmological can be local, sitting between us and the last scattering surface. The universe is not only a target, it is also a lens, a filter, and sometimes a masquerade. The lesson from earlier claims is methodological, not cynical, because the scientific process is designed for self-correction. A primordial signal must have the right frequency-dependence sky distribution and cross-checks across instruments. Multi-frequency maps are not optional, because dust is part of the universe too, and it must be treated as astrophysics, not as noise. As experiments improve, the target shifts from discovery to characterization, since a single detection is only the beginning of interpretation. If B modes are detected, we must measure their spectrum and scale dependence across multipoles. Inflation predicts a nearly scale-invariant tensor spectrum, with a tilt linked to R in simple models, and that link is a rare place where theory becomes crisp. That consistency relation is a key discriminator, because it ties the tensor slope to the dynamics of the inflating field. Many non-inflationary mechanisms do not obey it, or they produce tensors with different scale dependence and coherence. A measured violation would not just tweak inflation, it would redirect the origin story toward a different mechanism for generating perturbations. If B modes remain absent, the story still advances, because narrowing the allowed space is itself a form of knowledge. Tight upper bounds on R rule out broad regions of inflationary parameter space, including many steep potentials. They also constrain reheating histories, because reheating affects how moving scales map onto present observations, and it changes which part of the potential we're actually testing. The CMB also tests Big Bang ideas through non-Gaussianity, which asks whether the perturbations are truly a simple random field. The simplest single-field slow-roll inflation predicts almost Gaussian perturbations, with only tiny higher-order correlations. Many bounces, multi-field inflations, and phase transition scenarios predict larger, shaped non-Gaussian signals, because interactions and multiple degrees of freedom leave statistical scars. Non-Gaussianity is a fingerprint, not a headline, because its value lies in the shape of the correlation functions. Different shapes correspond to different interactions and field content, and they can distinguish, for example, local, equilateral, or folded configurations. Local-type non-Gaussianity is especially powerful because it changes large-scale clustering in ways galaxy surveys can test, turning statistics into a physical diagnostic. The CMB also offers a place to look for features and anomalies, which are small departures from a smooth power law. A pre-inflationary phase, a short inflationary duration, or a bounce can imprint oscillations or power suppression at the larger scales. Cosmic variance limits certainty, because we only have one sky, but it does not erase the search, especially when multiple datasets can be compared. Now we widen the channel beyond the microwave sky. Primordial gravitational waves need not show up only as CMB modes, because different early universe processes populate different wavelengths. Detectors listen in different bands, and each band corresponds to a different slice of cosmic history. The CMB is sensitive to ultra-low frequencies, set by the horizon at recombination, where wavelengths are comparable to the size of the observable universe. Space-based interferometers like LISA target millihertz frequencies, where millions of kilometers of baseline can track tiny changes in distance. Pulsar timing arrays target nanohertz frequencies, using the galaxy as a detector by monitoring the clock-like regularity of pulsars. These bands correspond to different physical scales and different cosmic epochs, so a signal in one band does not automatically imply a signal in another. Inflation can, in principle, produce a broad spectrum across frequencies because it stretches quantum fluctuations over many decades. But the amplitude depends on the energy scale and on how the spectrum tilts at small scales, and that tilt can be altered by post-inflationary expansion history. Phase transitions in the early universe are another source, and their gravitational wave signatures are more like a bell than a plateau. A first-order transition can nucleate bubbles that expand, collide, and stir the plasma into turbulence. That process produces a peaked gravitational wave spectrum with a characteristic frequency tied to the transition temperature and the expansion rate at that time. This is where particle physics meets cosmology with measurable consequences, because the microphysics determines the macroscopic signal. The standard model electroweak transition is likely a crossover, too smooth to generate a strong signal. Many beyond standard model theories make it first order, and gravitational waves become a test that complements colliders by probing the thermal history directly. Cosmic strings are a third source, and they are conceptually different because they are persistent objects rather than a brief event. They are one-dimensional defects or string-like objects that can form in symmetry breaking or in string theory constructions. A network of strings produces bursts and a stochastic background across many frequencies, through cusps, kinks, and loop decay. String signals depend on the string tension and reconnection probability, which control how efficiently the network loses energy. Pulsar timing arrays already constrain parts of that parameter space, and those constraints are becoming astrophysically competitive. A confirmed detection with the right spectral slope could point to strings or to other long-lived sources, so the spectral shape becomes the argument. The key is that gravitational waves bypass the opacity of the early plasma, and that is why they are so coveted. Photons last scattered at recombination, so they cannot show us earlier directly, only indirectly through initial conditions. Gravitational waves decouple essentially immediately, so they can carry information from far earlier times, if we can detect them and decode their origin. Yet even here, interpretation is hard, because the universe makes gravitational waves late as well as early. Astrophysical backgrounds from black hole binaries and other compact objects also fill the spectrum, and their populations evolve with cosmic time. The roadmap requires separating primordial signals from late-time populations through spectral shape, anisotropy, and cross-correlation with electromagnetic surveys. Next, we turn to the matter distribution itself, because the universe is a growth experiment running in slow motion. Tiny primordial perturbations became galaxies, clusters, and voids, and gravity amplified them in a way we can model. Large-scale structure surveys measure that growth and infer the initial conditions, turning maps of galaxies into constraints on the first moments. The power spectrum of matter is a transformed version of the primordial spectrum, filtered by radiation physics, baryon pressure, and dark matter dynamics. Its shape encodes the scalar tilt, running, and any features, and it also encodes the contents of the universe. In practice, every bump and slope is a negotiation between initial conditions and late-time evolution, so modelling must be both precise and humble. Baryon acoustic oscillations provide a standard ruler, a remnant of sound waves in the early photon, baryon fluid. They anchor distances and expansion history, which in turn affects how we reconstruct primordial scales from observed clustering. Weak lensing maps the integrated mass distribution and tests gravity on cosmic scales, adding a second, independent tracer of the same underlying structure. Large-scale structure is also sensitive to primordial non-Gaussianity, especially in the way galaxies trace dark matter on the larger scales. Local non-Gaussianity produces scale-dependent bias at very large scales, an effect that grows toward the largest modes. That is exactly where surveys can complement the CMB, because they sample many volumes and can reduce some forms of statistical limitation. Then there is 21 centimeter cosmology, which could become a second CMB in information content, but with three-dimensional reach. Neutral hydrogen emits or absorbs at 21 centimeters, and redshift turns that line into a layered map across cosmic time. It can probe the dark ages and cosmic dawn, when the first stars and black holes began to change the intergalactic medium. 21 centimeter data can access far smaller scales than the CMB, because it is not limited to a single surface like last scattering. That matters because many pre-Big Bang scenarios predict subtle deviations from scale invariance, sometimes strongest at small scales. It also matters because small-scale power constrains warm dark matter, early heating, and exotic energy injection, all of which would reshape the hydrogen signal. The promise is enormous, but the obstacles are real, and they are as much engineering as theory. Foregrounds in radio are bright and complex, dominated by our galaxy and by human-made interference, and calibration is brutal. Still, the prize is direct access to epochs before the first stars fully rework the intergalactic medium, when the cosmic gas still carried a relatively pristine memory. If we can map hydrogen across redshift, we can test inflationary initial conditions with unprecedented precision, because the number of measurable modes explodes. We can search for running of the spectral index and for small oscillatory features, which would hint at new dynamics near the beginning. We can also constrain isocurvature modes that would signal extra fields or pre-inflationary relics, tightening the link between cosmology and particle physics. Now we connect these observational channels to high-energy physics, because early universe history is a particle accelerator that no laboratory can match. Conditions in the first fractions of a second probe energies unreachable on Earth, and they do so repeatedly across the observable volume. The cosmos becomes the lab, and the sky becomes the detector, even when the underlying particles remain unseen. Dark matter is the most direct example, because it dominates the mass budget and shapes structure formation from the start. WIMPs were long favoured because thermal freeze-out naturally gives the right abundance, a coincidence sometimes called the WIMP miracle. But null results in direct detection and colliders push attention toward broader possibilities, including axions and hidden sectors with weaker couplings. Axions arise from the strong CP problem and from many string compactifications, so they sit at a crossroads of theory and phenomenology. They can be produced by misalignment and by topological defects, and they behave like a coherent field on large scales. Their mass and couplings determine whether they behave as cold dark matter, and whether they leave isocurvature signatures in the CMB. Isocurvature is a crucial bridge between particle candidates and inflation, because it tests whether more than one field mattered in the early universe. If axions exist during inflation, their quantum fluctuations can imprint isocurvature modes, shifting the relative perturbations between components. CMB limits on isocurvature then constrain the inflationary scale and the axion parameter space together, turning in non-detection into a two-sided bound. WIMPs connect differently, through freeze-out and through annihilation signatures that can affect the thermal plasma. Early universe expansion rates affect relic abundances, so modified pre-Big Bang histories can change the required cross-sections. A bounce or early kination phase can shift the thermal story, altering which particle models remain viable without changing their laboratory signatures. Relic particles are also messengers of reheating. The era when inflation's energy became a hot bath of standard particles, the reheating temperature sets which species were ever in equilibrium, and it controls how quickly the universe became radiation-dominated. It affects dark matter production, neutrino decoupling details, and the viability of baryogenesis mechanisms, so it is a hinge between cosmic history and microphysics. Baryogenesis is the next constraint, because the universe contains more matter than antimatter, and that asymmetry is not optional. The standard model cannot easily generate the observed asymmetry with sufficient CP violation and out-of-equilibrium dynamics. So the early universe must host new ingredients or new phases, and cosmology becomes a test of ideas that particle experiments only partially access. Leptogenesis is a leading framework where heavy neutrinos decay and create a lepton asymmetry that is later reprocessed. Electroweak processes then convert part of it into baryon number, using known standard model anomalies as machinery. This ties the cosmic matter excess to neutrino mass generation, and to physics at very high scales, giving the neutrino sector an outsized role in the origin narrative. Electroweak baryogenesis is another route, but it demands a first-order electroweak phase transition, a new CP violation beyond what we have measured. That demand is testable in multiple ways, which is why it remains compelling despite its difficulty. Collider searches probe new particles, while gravitational wave detectors could probe the transition itself, offering a rare cross-check between sky and accelerator. Neutrino properties also shape cosmological observables directly, even if neutrinos never form galaxies. The sum of neutrino masses suppresses small-scale structure by free streaming, subtly smoothing the matter distribution. The effective number of relativistic species, NERF, changes the expansion rate during radiation domination, and shifts CMB and BBN predictions, making it a sensitive dial for hidden physics. Extra-light species are a window into hidden sectors and quantum gravity relics, because they behave like additional radiation in the early universe. A deviation in NRSLF would imply new degrees of freedom in the early universe, and it would demand a consistent thermal history. It would also constrain reheating and any pre-Big Bang scenario that changes the radiation content, because energy must be accounted for somewhere. Even the lithium anomaly from nucleosynthesis remains a pressure point, because it resists a simple resolution. It could be astrophysical, or it could hint at new physics affecting BBN such as late decays or altered reaction rates. Either way, it reminds us that early universe tests are a network, not a single measurement, and consistency across that network is the standard. At this stage, the roadmap becomes a logic tree, where different branches are pruned by different datasets. Inflation, bounces, and quantum boundary proposals make overlapping predictions for the scalar spectrum, which is why the debate persists. They diverge most sharply in tensors, non-Gaussianity, isocurvature, and spectral features, because those observables are harder to mimic without committing to specific dynamics. A high-confidence primordial B-mode detection would be a turning point, not because it would end debate, but because it would anchor it. It would indicate a quantum origin for metric fluctuations in a high-energy scale, tightening the connection between gravity and quantum theory. It would also force bounce and ekpyrotic models to explain how tensors were generated or why the signal is not primordial, sharpening what before must accomplish. A strong null result on R, combined with tight non-Gaussianity bounds, would also be decisive because it would remove many flexible constructions. It would favour low-scale, simple inflation or mechanisms that mimic its predictions with minimal extra fields. It would also squeeze many strongly coupled bounce models and many multi-field constructions where interactions tend to leave detectable higher-order correlations. A gravitational wave background peaked in the Lisa band would point to phase transitions, not to the simplest inflation, and it would imply new thermal physics. A nanohertz background with a cosmic string-like spectrum would resurrect defect physics as an origin clue, and it would demand a consistent network evolution. Each detection would narrow the story by identifying the engine, and by forcing the rest of cosmology to accommodate it. A precise 21 centimeter measurement of small-scale power could test running and features beyond Planck's reach, because it samples modes the CMB cannot resolve. It could also reveal early heating or exotic energy injection, which would constrain dark matter interactions and astrophysical sources. It would turn the Dark Ages into a precision era, and it would make initial conditions a measurable object rather than an assumption. Across all these channels, the hardest work is not building instruments, although that work is formidable. The hardest work is controlling systematics and foregrounds without biasing the answer, because subtle errors can masquerade as profound discoveries. The universe is loud, and the primordial signal is quiet, so the discipline is to let the data speak without coaching it. This is where earlier chapters return with teeth, because philosophical flexibility meets experimental rigidity. The measure problem in eternal inflation is not solved by better telescopes alone, since it is partly a question of how probabilities are defined, but sharper data can rule out potentials and reheating histories that make the multiverse claim flexible to the point of emptiness, forcing the theory to earn its explanatory power. The border Guth, Vilenkin past incompleteness result also returns as a constraint, not a conclusion, and it shapes what before must mean. If inflation is past incomplete, then some boundary condition or pre-inflationary phase still matters, even if it is brief. Observables can tell us whether that boundary left any trace, an imprint in curvature, features, or correlations that refuse to be erased. Quantum cosmology proposals face the same demand, because elegance is not evidence unless it predicts what we see. A no-boundary or tunneling condition must translate into a predicted distribution of perturbations and curvature, not just a narrative of origin. If it cannot, it risks becoming a story about beginnings that never meets the sky, and the sky is where cosmology ultimately lives. So the climax is not a single experiment, because nature rarely yields to one decisive measurement. It is the convergence of independent probes that attack the same unknown from different sides, reducing the space for coincidence. Photons test the last scattering surface, matter tests growth, gravitational waves test the earliest dynamics directly, and their agreement, or tension, becomes the verdict. Now the narrative turns from what we can test to what it would mean to finish the test. Even perfect data may not answer what caused the laws, or why there is something rather than nothing, because those questions may not be physical in the usual sense. Science can still tell us whether a proposed before is real or only verbal by demanding consequences that survive contact with observation. A final answer in cosmology might be a boundary principle, not an earlier event, because time itself may be part of what is explained. It might be a symmetry that makes the beginning a surface, not a moment, and that turns initial conditions into a derived concept. Or it might be a demonstration that some questions cannot be posed inside time at all, an answer that is less like a date and more like a rule. We end with the central question sharpened by the roadmap, and by the discipline of measurable claims. If the Big Bang is the earliest chapter we can currently read, what would count as evidence of a previous page, rather than a reinterpretation of this one? The final chapter confronts the limit where explanation becomes definition, and where physics decides what it can mean by origin. We reframe the question into tests, because what came before may be a category error if time itself is dynamical. Did spacetime begin, or is before undefined when the metric and causal order are not yet classical? If there is no beginning, What replaces it? Eternal inflation, a bounce, or emergent time that condenses from deeper degrees of freedom? If there is a beginning, what boundary rule selects it? Like the no-boundary proposal or tunneling quantum creation from a compact Euclidean-like geometry, inflation plus reheating fits the CMB and large-scale structure, painting a vivid scene of quantum ripples stretched across a rapidly expanding sky.